Hello there, and welcome to Science for Sleep, where curiosity gets cozy and the stars wait patiently for our attention. Tonight, we're drifting through a question as wide as the galaxy itself, one that's been whispering to human imagination for as long as we've looked up at the night. How many planets are in our galaxy? It sounds like a simple question, something you might expect to have a neat number attached. But the truth is much softer, much larger, and far more mysterious than any tidy answer. The sky is not just a canvas of stars, it's a map of possibilities, a quiet reminder that the darkness above is not empty, but full of invisible worlds. Some of them may look like ours, blue and cloud-streaked, while others might be made of metal, ice, or boiling storms. Some travel faithfully around their suns, and some drift alone, wandering the cold between stars. Before we start our journey, wherever you are, take a slow breath and notice your own small patch of the universe. Maybe it's night outside your window, or maybe you're listening while the day hums on beyond your curtains. Either way, the same galaxy arches over you, the same spiral of light and dust we all belong to. Somewhere in that sweep of starlight, countless worlds are turning, unseen but not unfelt. If you find this quiet exploration soothing, or it helps your thoughts settle a little, it would mean a lot if you like this video or subscribe to this sleepy corner of science. It helps others find a bit of calm too. Now let's begin. Not with numbers or telescopes just yet, but with the simple act of looking up. The night sky, to the naked eye, seems almost still. Maybe you see a few hundred stars if the air is clear and the city lights are kind. Each one, a point of light from some distant sun, a pinprick through the darkness. It's easy to forget that each of those stars could have a family of worlds orbiting around it, circling like invisible dancers around a hidden fire. What we see as a single glimmer might in reality be a whole solar system. Planets of gas and rock and ice moving in endless rhythm, their surfaces warmed, frozen, or storm-lashed depending on their distance from the light. Our own sun has 8 such companions, and that small neighbourhood already feels enormous to us. Multiply that by the hundreds of billions of stars in the Milky Way, and you begin to sense the scale we're stepping into. When you stand beneath the stars, you're not just looking at lights, you're looking at potential homes, not for us necessarily, but for themselves. Self-contained worlds with their own skies, their own histories, their own secrets. Some might cradle life in forms we can't imagine. Others might be nothing more than frozen stones spinning forever in the dark. But every single one contributes to the quiet richness of the galaxy, to that vast sense of something happening everywhere at once. Humans have been thinking about this for longer than science has existed. Long before telescopes or spacecraft, we looked at the heavens and wondered if other worlds were out there. The earliest stargazers saw the wandering lights we now call planets and imagined them as gods, messengers, omens, or symbols. The night sky wasn't just a map of navigation, it was a theatre of meaning. And even though our understanding has changed, the feeling hasn't gone away. When we ask how many planets are in our galaxy, what we're really asking is whether we're alone in this cosmic sprawl, and whether the stars are as full of companions as our hearts hope they are. But this question isn't only about emotion. It's a scientific puzzle, one that astronomers have been working on with increasing precision. The answer lies hidden in patterns of light, in tiny dips and wobbles measured across years of patient observation. Each new discovery adds another dot to a map that keeps expanding, and with every addition the galaxy feels less like a distant abstraction and more like a bustling community. When you hear the number of planets estimated to exist, billions upon billions, it can be hard to picture. But you can start by imagining this. For every grain of sand on every beach on Earth, there may be thousands of planets out there in the Milky Way alone. That's not poetic exaggeration. That's data. That's what we've begun to see through the eyes of our machines and the quiet calculations of light. Still, we should start small, close to home. Our solar system is a perfect example of what a planetary family can be. 8 main planets, a swarm of moons, dwarf planets, comets, and asteroids. It's a complex, dynamic place. Each world's so different that they almost seem like species, each with its own character and climate. Mercury scorched and cratered, Venus suffocating under its own heavy atmosphere. Mars red and silent, but still holding secrets in its frozen soil. Jupiter, a churning ocean of gas. Saturn draped in rings of ice and rock. Uranus tilted like a rolling marble, and Neptune deep blue and distant. Then there's Earth, quietly spinning, full of oceans and forests and everything listening right now. If just one star, our Sun, can host so much variety, then multiply that imagination across the galaxy. That's what astronomers are doing. They look at stars and see not just points of light, but systems. Some stars might have 1 or 2 planets, some might have dozens, and some may have none at all, lonely travellers burning alone in the dark. The distribution is uneven, but the pattern is unmistakable. Planets are common. They're not rare jewels scattered here and there. They're the natural byproduct of star formation, a consequence of gravity and dust doing what they do best: clumping, spinning, creating. When a star forms, a swirling disk of material gathers around it. Out of that disk, small grains collide and stick together, forming rocks, then mountains, then worlds. It's not an exception. It's a rule. That means our solar system isn't special in its architecture, only in its familiarity. Every time a new star is born, there's a good chance a handful of planets will accompany it. That's why astronomers sometimes call planets the inevitable children of stars. The more we study the galaxy, the clearer this becomes. We used to think other planetary systems might be unusual. Now we know they're the norm. What's rare isn't the presence of planets, but the absence of them. When you think of the Milky Way, think of a spiral city of stars stretching 100,000 light-years across. In that city, the Sun is one among hundreds of billions. If even half of those stars host planets, and the evidence suggests it's more than that, you're looking at hundreds of billions of worlds. Some orbit close, basking in heat. Others drift far out where the light fades to a dim ember. Some circle red dwarfs that will burn for trillions of years, far longer than our own Sun will live. Each system is its own story, unfolding silently, perhaps with moons and weather and seasons, perhaps with nothing but frozen rock and empty wind. But to count them, to even estimate them, we had to learn how to see the invisible. For most of history, the existence of other planets was pure speculation. Our telescopes could see stars, but not the tiny dots orbiting them. Even the nearest ones were too small, too dim. Imagine trying to spot a firefly next to a lighthouse from 1,000 miles away. That's the scale of the problem. The light of a planet is drowned out by the brilliance of its star. For centuries, that blindness defined our limits. We knew the stars were there, but not what surrounded them. That changed only recently, within living memory. The first detection of a planet orbiting another star came in the 1990s. Before that, the idea was little more than hope. Once it was confirmed, the floodgates opened. We started finding them everywhere. Each discovery sharpened our understanding, and soon we realized something extraordinary. The galaxy isn't sprinkled with rare planets. It's teeming with them. Everywhere we look, we find evidence of worlds, sometimes unlike anything in our solar system. Giant planets orbiting close enough to their stars to scorch, small rocky ones hugging faint red suns, and others so far away that their orbits take centuries to complete. When you think about all those possibilities, the night sky changes character. It stops feeling like a flat dome of stars and starts to feel like depth. Every point of light becomes a potential system. Every one of those could have its own array of planets, moons, and perhaps even life. The realization is humbling and thrilling all at once. It doesn't make Earth smaller, but it does make the universe larger in our minds, and that, strangely, brings a kind of peace. Knowing that we're part of something vast and continuous, that our world isn't an isolated island, but one among countless others, gives a perspective that's both grounding and freeing. Our ancestors used to tell stories about the stars because they couldn't see the worlds around them. They invented myths to fill the silence. Now, with the help of science, we can begin to replace some of those myths with knowledge. But the wonder remains the same. The language has changed, from gods to gravity, from prophecy to probability, but the curiosity that drives us is ancient. Every new planet we discover answers one question and opens 10 more. What are they made of? How old are they? Do they have atmospheres? Could they support life? Each one is a step deeper into a mystery that may never end, and that's part of what makes it beautiful. When we say, how many planets are in our galaxy, we're not just asking for a number. We're asking for a sense of belonging in a place so large it defies comprehension. The Milky Way holds its planets like a sea holds its waves, too many to count, all part of the same movement, forming and reforming through time. The stars are just the bright markers. The planets, though mostly hidden, make up the real landscape. If you could somehow see them all at once, the galaxy would not look like a scattering of stars. It would look full, textured, and alive with orbits. The invisible would outnumber the visible by orders of magnitude. There's a quiet comfort in that thought. Somewhere, perhaps right now, another planet is turning toward its sunrise. Maybe it has clouds drifting across its sky, or mountains catching the first light of its day. Maybe it's nothing like Earth at all, thick with ammonia storms or buried under ice. But it exists, as real as the ground under your feet. Multiply that by billions, and the Milky Way becomes not just a galaxy, but a collection of countless mornings, each unfolding unseen across space. And here we are, one small species on one small world, counting. Not because counting will ever capture it all, but because it helps us understand our place in the pattern. The act of asking is what connects us to it. We may never know the exact number of planets in our galaxy, but we're learning enough to know that they are not rare, and that alone changes everything. The sky above isn't distant anymore. It's full of neighbours we can't yet visit, but perhaps someday will. If you were to look out into the Milky Way from far beyond it, you'd see its spiral arms stretched out like soft ribbons, filled with stars and dark clouds of dust. Hidden within those clouds are the seeds of new stars and new planets forming even now. Worlds being born while you listen. The galaxy is alive with creation. It's not static or frozen. It's in motion, always shaping itself. That means the number of planets isn't fixed. It grows slowly but steadily as time unfolds. Somewhere a disk of dust is spinning around a young star right now, and inside that disk tiny grains are colliding, sticking together, becoming pebbles, rocks, and eventually mountains. Give it a few million years, and it will become a new world. The galaxy never stops making them. That's the quiet miracle of it all. Even while you sleep, new planets are coming into existence. The universe is busy, tireless, endlessly generative. And though we may never see most of those worlds, they exist all the same. That's what makes the night sky such a comforting thing to look at. Every point of light and every patch of darkness hides something in progress, a story that's still unfolding, just like ours. Somewhere in that gentle sprawl of stars in the long sweep of the Milky Way are billions of homes we'll never visit, billions of places that we'll never know we existed, and yet they are part of the same universe that made us. We are built from the same materials, the same stardust and gravity that shaped them. When we wonder how many planets there are, we're really wondering how far our own story extends, how deep the roots of life might go into the fabric of space. And so the question lingers, not as a puzzle to solve once and for all, but as a doorway into everything that follows. The galaxy is vast, and tonight we've only begun to step into it. When you look up at the sky, what you see is only the faintest whisper of what's really there. The night appears scattered with stars, but even in the clearest air, even under the darkest desert sky, your eyes can only catch a few thousand points of light. It feels like a lot until you remember that there are hundreds of billions of them in our galaxy alone. The rest are hidden, too faint or too distant for your eyes to notice, their light stretched thin across the expanse of space. But they are there, steady as heartbeats, each one a sun in its own right, and many of them surrounded by invisible companions that never glow, never shine, and yet make up most of what the galaxy truly is. If you could see through the glare, through the distance, through the limits of human vision, you would notice that the sky isn't just a field of dots. It's a vast, living structure. Stars are not evenly sprinkled across the cosmos. They're gathered into swirling bands and clusters, woven together by gravity. The Milky Way itself, the band of pale light that arches faintly overhead, is only the edge-on view of our galactic home. What looks like a soft smudge to the naked eye is really billions of suns layered together, light upon light, too distant to separate. It's not a stripe of mist, it's our neighbourhood seen from within, and each of those stars, however faint, could be surrounded by its own retinue of planets. The thought is easy to say, but hard to grasp. We've spent most of human history thinking of planets as rare. Until a few decades ago, we knew of only the ones orbiting our own sun. That was our entire sample size. 8 main planets, plus some moons and smaller bodies. Everything else was speculation. It wasn't that astronomers didn't imagine other worlds. They did, often passionately. But there was no proof. The stars were too far, the planets too dim. So, for centuries, we simply didn't know. The telescope helped us understand the scale of the universe, but it didn't reveal planets beyond our solar system. Even with the most powerful glass lenses and mirrors, exoplanets remained invisible. Their stars blazed too brightly, drowning out any hint of a companion. Imagine trying to see a candle next to a searchlight from thousands of kilometers away. That's what astronomers were up against. The idea of counting the galaxy's planets seemed impossible, something that belonged to philosophy more than science. But curiosity, as it tends to, refused to let go. Astronomers began to wonder if they could detect planets without seeing them directly. After all, planets pull on their stars. They make them wobble ever so slightly. The light from a star shifts in colour as it moves toward and away from us, a kind of cosmic breathing. With the right instruments, those minute shifts can be measured. It's an act of extraordinary patience, watching the same point of light night after night, year after year, to see if it trembles. And when it does, that tremble tells a story. Something unseen is tugging on it. Something with mass. Something in orbit. The first time that trembling was confirmed beyond any doubt, the world changed. It meant that planets existed elsewhere, not as a dream, but as a measurable reality. And if one star had planets, others almost certainly did too. The flood of discoveries that followed was astonishing. Within just a few years, dozens of exoplanets had been identified. Now there are thousands, each one confirmed by precise measurements of light and motion. Some are enormous, others small and rocky, but together they form a growing catalogue that hints at the galaxy's true abundance. Every new discovery reshaped our sense of the night sky. Suddenly, those dots above us weren't just distant fires. They were solar systems. Each star became a centre of gravity, a sun with its own collection of worlds. Some may have multiple planets orbiting in complex harmony. Their orbits intertwined like threads in a pattern too large to see. Others may have just one, circling quietly in the dark. But when you consider the scale, hundreds of billions of stars, and multiply that by the likelihood of planets, the result is staggering. Even conservative estimates suggest there are at least 100 billion planets in our galaxy. Many astronomers think the real number could be closer to 1 trillion. Numbers like that are hard to imagine. The human mind isn't built for them. We can picture 10, maybe 100, even 1,000 if we try. But 1 trillion worlds, each one potentially unique, each with its own chemistry, its own sky, its own weather, that's beyond comprehension. And yet, it's real. The galaxy is not empty space dotted with light. It's a vast ocean of worlds. Think about that for a moment. Every patch of sky you've ever seen, no matter how small, contains not just stars, but likely thousands of planets. Even the empty-looking areas between stars, those dark stretches you might think are voids, are filled with distant systems too faint to see. The night sky, if you could somehow tune your eyes to all wavelengths of light, would blaze with detail. Clouds of dust, newborn stars, dying suns, and around them countless planets spinning in silence. When astronomers point their instruments at a seemingly unremarkable region of space, they often find more than they expected. The Hubble Deep Field image, for example, focused on a tiny dark patch of sky, smaller than a grain of sand held at arm's length, and revealed thousands of galaxies. Not stars, galaxies. Each of those galaxies likely holds hundreds of billions of stars, and each of those stars likely has planets. If our own Milky Way is typical, the total number of planets in the observable universe becomes impossible to articulate. But here, tonight, we're staying close to home. One galaxy is enough wonder for now. Within our own Milky Way, the stars are not evenly spread. Most of them are packed into the disk, the flat plane that forms the spiral arms. That's where the action happens, where stars are born from gas and dust clouds, where gravity gathers matter into new suns and worlds. The Sun, and by extension, Earth, sits within one of those arms, about halfway between the centre and the edge. When you look up and see the Milky Way stretching across the sky, you're seeing that disk from the inside, like looking through a long glowing tunnel. Every point of light in that band could be a home to planets. If we could travel outward from our position, we'd pass through regions filled with stars like ours, many of them orbited by planetary systems. Some would be stable, others chaotic. Some might have multiple suns. Binary or even triple star systems are common, and they can host planets too. In some of those places, the sky would never be dark. 2 or 3 suns might rise and set, casting overlapping shadows. Imagine living on a world where day and night aren't predictable, where light changes colour as one sun sets and another takes its place. It sounds like science fiction, but astronomers have found such systems. The diversity of these worlds is extraordinary. We've found gas giants larger than Jupiter, orbiting closer to their stars than Mercury is to the Sun. We've found rocky planets twice the size of Earth, orbiting cool red dwarfs. Some planets orbit stars that are near the ends of their lives, swollen into red giants. Others circle young, unstable stars surrounded by the remnants of the disks they were born from. Each new detection expands the definition of what a planet can be. But even with all that data, we've only seen a fraction of what's out there. The methods we use to find planets favour certain kinds over others. It's easier to detect large planets close to their stars because their gravitational influence is stronger, and their transits, those tiny dips in starlight when they pass in front of their suns, are easier to spot. Small, Earth-sized planets in wide orbits are much harder to detect. That means our current count, as impressive as it sounds, is only the beginning. There are likely far more planets waiting to be found, especially the smaller, subtler ones that don't reveal themselves easily. Astronomers often describe the search for planets as listening for whispers in a noisy room. The signals are faint and fleeting. A single detection can take years of confirmation before it's accepted as real. But once confirmed, it becomes part of a growing map, a chart of the invisible architecture of our galaxy. And that map, slowly filling in, tells a consistent story. Planets are not rare exceptions. They are the rule. In recent years, advances in technology have allowed us to detect planets that are truly Earth-like in size and orbit. These are the ones that capture the most attention, the so-called habitable zone planets where liquid water could exist. They are still distant and unreachable, but their discovery changes the emotional landscape of astronomy. It turns the question of whether Earth is unique into something else entirely. How common is a world like this? The answer, based on current data, is surprisingly optimistic. Estimates suggest there could be tens of billions of potentially habitable planets in our galaxy alone. Tens of billions of places where oceans might glimmer under alien suns, where atmospheres could hold clouds and rain, where the conditions for life might quietly exist. To think of all those worlds spinning silently is humbling. The night sky ceases to be a backdrop. It becomes a vast, ongoing process, a living pattern of creation. The stars are the visible part, but the planets, those countless unseen dots, are where the stories unfold. They are where matter becomes landscape, where chemistry becomes weather, and perhaps where life, in all its improbable variations, begins to stir. What makes the thought so profound is how recent it all is. For most of human history, we didn't know any of this. We saw stars and imagined stories, but we couldn't confirm whether they had worlds. In just a few decades, that ignorance has turned into knowledge. The transition is still underway, and it's reshaping how we see our place in the universe. We're no longer isolated. We're one planet among billions, orbiting one star among billions, in a galaxy among billions more. It's a truth that's both dizzying and peaceful. When the night feels large, when the silence between stars seems infinite, it helps to remember that the darkness isn't empty. It's full of orbits, paths, and worlds, too small and faint to see, but too numerous to ignore. Each one adds to the quiet complexity of the cosmos, a complexity we're only beginning to glimpse. The stars above you right now, even the faintest ones, likely have companions you can't see. Somewhere around them, a planet is turning, its day beginning or ending, its skies lit by a sun you'll never see rise. That's what those countless dots really represent. Not just stars, but potential homes. Each point of light a story in progress, each with its own unseen chapters. The galaxy isn't just full of stars, it's full of worlds. And knowing that changes how we see the night. It's no longer just a spectacle. It's a reminder that the universe is not a place of absence, but of abundance. The more we learn, the more the darkness glows with meaning. As you listen now, somewhere across the Milky Way, new planets are being born. Dust is gathering into clumps that will one day become mountains and oceans. Stars are igniting, systems are forming, and in that slow, steady process, the galaxy continues its quiet expansion of worlds. The sky above us, the one that seems so still, is in constant motion. Every star, every planet, every bit of light and dust is moving, orbiting, changing. We live inside a cosmic dance that's been ongoing for billions of years. We can't see it all yet, but we're learning to listen. Every measurement, every detection, every faint flicker of light adds another piece to the puzzle. The galaxy may never reveal all its worlds to us, but even knowing that they're there is enough. It gives the night a new dimension, a sense of fullness that wasn't there before. The countless dots above us are no longer distant strangers. They're neighbours, quiet and far away, but part of the same vast story we're in. Long before telescopes, long before electricity or equations, there were eyes turned toward the sky and minds trying to make sense of what they saw. When the world was still small and surrounded by mystery, the heavens offered a kind of quiet instruction. People watched the slow drift of stars, the rise and fall of the moon, the wandering lights that behaved differently from the rest. Those wanderers became the first known planets, though the word itself did not yet exist. To early observers, they were divine, moving points of light that refused to stay fixed among the others. They were the strange ones, the exceptions, the signals that the sky was not entirely still. Every culture that looked up saw patterns there. Some imagined hunters, animals, spirits, or stories written in the constellations. Others saw maps for planting, fishing, or travelling. The sky was both calendar and compass. It ordered life on Earth. But behind that practical use lay a deeper curiosity. The ancients wanted to know what those moving lights were. They looked different from stars. They changed position night after night, and sometimes they even reversed their motion in the sky. To human eyes unused to the concept of orbit, that reversal looked like intention. Something in the heavens seemed alive, thinking, perhaps even watching. The earliest records we have show that the Babylonians, around 3000 BCE, carefully charted these wandering lights. They noticed their patterns, the way they looped and reappeared, and they began to predict their movements. They didn't yet think of them as worlds. To them, the sky was a dome over the earth, and those lights were celestial gods moving through it. Each one carried meaning. Mars was red, so it became associated with war and blood. Venus shone brightly near sunrise and sunset, so it became linked to love and beauty. Jupiter moved steadily, massive and slow, and was treated as a symbol of power and authority. The planets were characters in a cosmic story, their paths shaping the fates of kings and kingdoms. Egyptians, Chinese, Indians, and the peoples of Mesoamerica all watched the same wandering lights and developed their own interpretations. To the Mayans, the motions of Venus were so important that entire calendars were built around them. They could predict its appearances with astonishing accuracy. Across the world, astronomers in early civilizations became mathematicians almost by necessity. To predict the sky, they needed to learn rhythm, pattern, and recurrence. And by following those patterns, they began to suspect that the heavens were not random, but governed by laws that could perhaps be understood. The Greeks were among the first to turn that suspicion into philosophy. They gave us the word planet from planets, meaning wanderer. To them, these lights were not divine messengers, but celestial objects moving according to some natural order. The philosopher Anaximander suggested that the Earth might be floating freely in space rather than resting on something solid. That was an astonishing thought in a time when most people still pictured the world as a flat surface covered by a dome. Then came Pythagoras, who believed the heavens moved according to mathematical harmony. He imagined the planets and stars producing a kind of music as they moved, an idea that blended science and mysticism but hinted at something profound, that the cosmos could be described by numbers. By the 4th century BCE, thinkers like Eudoxus and Aristotle were proposing elaborate models of spheres rotating around the Earth. They didn't yet know that the sun was at the centre. To them, Earth was fixed and everything else revolved around it. This geocentric view made sense given what they could observe. After all, the ground felt still. The stars seemed to move across the sky together, and only the planets wandered among them. To explain that wandering, they invented systems of concentric circles within circles, each carrying a planet along its path. The models grew more complex over time, but they worked well enough to predict the movement seen from Earth. Accuracy, not truth, was the goal. Then came the mathematician and astronomer Claudius Ptolemy in the 2nd century CE. His model of the cosmos placed Earth at the centre, surrounded by nested spheres carrying the moon, the sun, the planets, and finally the stars. The stars were thought to be fixed on a distant crystalline sphere that turned once each day. It was a vision of the universe as a grand machine, elegant and closed. For over 1,000 years, Ptolemy's model would dominate how people understood the heavens. It was detailed, mathematical, and reassuringly complete. But it was also wrong. The planets didn't move in perfect circles, and Earth was not the centre of their dance. Still, within the limits of human perception, the illusion was convincing. For centuries that illusion held. Observers tracked the planets, calculated eclipses, built calendars, and aligned temples and monuments to celestial events. The sky was a clock that could be read but not yet questioned. The early dreamers of the cosmos had curiosity but not the tools to test it. They understood patterns but not yet causes. Their world was bounded by philosophy and faith, and within those boundaries they imagined the heavens as perfect and unchanging. The Earth, by contrast, was flawed and temporary. That division between celestial perfection and earthly imperfection shaped human thought for millennia. Still, the dream of otherworld persisted quietly in the background. Even within the old frameworks, a few voices wondered whether the wandering lights could be places, not just lights. Some philosophers proposed that other stars might be suns like ours, each with their own worlds. The Greek thinker Epicurus suggested that the universe was infinite and filled with countless worlds, some like Earth, others entirely different. He had no evidence, only reasoning, but his argument was startlingly modern. If nature could make one world, why not many? If atoms were infinite, then their combinations could be infinite too. It was an early glimpse of what we now call the cosmological principle, the idea that our place in the universe is not unique. That thought was dangerous in times when the heavens were considered sacred. For much of history, to suggest that other worlds existed was to challenge religious and philosophical order. The heavens were divine, Earth was human. To say that there might be other Earths, perhaps even with their own beings, blurred that boundary. Yet the idea refused to die. It survived in poetry, in philosophy, and in secret speculation. The early dreamers didn't just map the sky, they imagined what lay beyond it. When you look at the earlier star maps or the carved stone observatories of ancient cultures, you see the first steps in a story that leads directly to the question of how many planets there are in our galaxy. Those early observers couldn't know what they were really looking at, but they built the foundation of curiosity. They proved that careful watching could reveal order in apparent chaos. They learned that the universe repeats itself, that the same lights return in the same places, that the heavens can be studied rather than feared. From that understanding, everything else followed. The invention of geometry and the study of motion grew partly from these efforts. By measuring the paths of stars and planets, early scientists developed mathematical tools that still underpin modern astronomy. The idea that nature could be understood through pattern, ratio, and prediction was revolutionary. It shifted the human relationship with the sky from reverence to inquiry. The heavens were no longer an unreachable realm. They were a system waiting to be decoded. When the first lenses were ground into glass in the late Middle Ages, the world of astronomy changed again. Telescopes turned speculation into observation. What had been points of light became disks, moons, and shadows. When Galileo pointed his small telescope toward Jupiter in 1610, he saw 4 tiny lights moving beside it. They weren't stars, they were moons circling a planet. It was the first undeniable proof that other bodies had their own systems. Jupiter, in miniature, was like a second solar system. That discovery shattered the notion that everything revolved around Earth. It suggested that motion and order existed elsewhere too, independently. The early dreamers could never have imagined what Galileo saw. To them, planets were divine symbols, not physical places, but the line between dream and discovery is thin. Without their curiosity, without their persistence in watching, measuring, and wondering, the leap to telescopic observation might not have come when it did. They created the intellectual soil from which modern astronomy grew. Across centuries, the idea of other worlds evolved. In the time of Giordano Bruno, the 16th century philosopher who believed that every star was a sun surrounded by planets, the dream of infinite worlds returned in full force. Bruno paid for that idea with his life, condemned for heresy. But his vision, that the universe was filled with innumerable suns and worlds, was closer to the truth than anyone then could prove. His dream was scientific heresy but cosmic realism. It would take generations for evidence to catch up with imagination. Yet, through all the centuries between Ptolemy and the first exoplanet discovery, one thread remained constant: the desire to understand what lay beyond our sight. That desire drove sailors to navigate by the stars, builders to align temples with solstices, and philosophers to argue about the nature of the cosmos. The early dreamers may not have had telescopes or data, but they had something just as powerful: a willingness to wonder, to stay awake under the stars and ask, "What is all this for?" without expecting an answer. Their questions shaped the path that would eventually lead to the discovery of thousands of worlds beyond our sun. They gave us the first vocabulary for thinking about the cosmos. Words like orbit, sphere, harmony and motion began as philosophical ideas before they became physical ones. By seeking patterns in the heavens, they unknowingly prepared us to see patterns in other stars, to look for the subtle signs that might reveal planets we can't see. The lineage of those dreamers runs straight through the centuries, from Babylonian star watchers to Greek philosophers, from Arabic astronomers refining mathematics to Renaissance thinkers questioning ancient authority. Each generation passed on a piece of the puzzle. They didn't have the tools to find planets in other systems, but they laid the groundwork for those who would. The story of counting planets begins not with telescopes or satellites, but with eyes and patience. When we ask today how many planets are in our galaxy, we're carrying forward that same curiosity, only with better instruments. The question hasn't changed, only our ability to answer it has. Those ancient observers could not have imagined the machines we now send into orbit, the data we gather from space telescopes, or the algorithms that sift through starlight looking for a faint dip that signals a planet. Yet their impulse, to watch, to measure, to seek order in the night, is exactly the same. The technology is new. The wonder is ancient. The early dreamers remind us that curiosity is a form of continuity. Every time we look up, we're participating in something that stretches back tens of thousands of years. The same stars that once guided nomads across deserts now guide spacecraft across the void. The same constellations that told stories to farmers now anchor our telescopes. We've replaced myth with mathematics, but the sense of awe remains. That awe is what keeps the story moving forward from one era to the next, from wondering about the moving lights to understanding them as worlds. And so the thread continues. From those early dreamers grew the foundation of astronomy itself, the quiet beginning of a question that would grow until it filled the galaxy. The night sky they saw is the same one we see, only now we know more about what hides within it. The wanderers they named as gods are planets we can describe in terms of rock, gas and ice. What hasn't changed is the feeling that started it all, the simple human impulse to look up and imagine what might be out there. The story will move on from here into the centuries when that imagination turned into discovery, when mathematics and observation finally revealed the true structure of the solar system and beyond. But even as science advanced, the spirit of those early watchers remained at its core. Their wonder, carried quietly through time, still echoes in every question we ask about the worlds beyond our own. The picture of the universe that early thinkers held began to shift quietly, not with sudden revolution at first, but through slow accumulation of observation and courage. The world was changing in the centuries between the late Middle Ages and the dawn of modern science. Instruments improved, navigation demanded better understanding of the heavens, trade, travel and exploration brought new ideas into conversation, and somewhere within that growing network of thought, the old celestial order began to tremble, the ancient image of concentric spheres, each carrying a planet around the unmoving Earth, had lasted for almost 2,000 years. It was simple, orderly, and deeply comforting. Everything had its place. The heavens were pure, the Earth was central, and human beings stood at the heart of creation. But the sky itself was patient and indifferent to philosophy. Over time, the small discrepancies between what people believed and what they actually saw began to add up. The planets did not move with perfect regularity. They drifted in ways that didn't fit cleanly into the models. Mercury and Venus stayed close to the Sun, Mars and Jupiter wandered in wider arcs, and sometimes they appeared to slow down or even move backward against the background of stars. Those small inconsistencies would eventually undo centuries of certainty. By the 15th century, a Polish scholar named Nicholas Copernicus began to reimagine the structure of the cosmos. He studied mathematics, astronomy, and medicine, and quietly gathered notes on the motion of the planets. His work was cautious and methodical. He wasn't trying to overthrow the world's understanding of itself. He was simply trying to make sense of the data. The numbers didn't fit unless one assumption was changed, unless the sun, not the Earth, was at the centre. When he shifted the viewpoint, everything became simpler. The retrograde motions of planets, those strange backward loops, vanished as illusions. The orbits lined up in a harmony that had been missing from the old models. It took decades for him to publish what he found. The idea was dangerous, not only to religious authority but to human pride. The notion that Earth moved, that it was just one planet among others orbiting the Sun, felt like a demotion. But in 1543, the year of his death, Copernicus finally released his book on the revolutions of the celestial spheres. It was dense, mathematical, and understated, but its implications were seismic. It said that we were not the centre of creation. We were travellers in a vast cosmic system, moving with all the others. For generations, his idea remained more mathematical than philosophical. Scholars treated it as a convenient model, not necessarily as truth. It made calculations easier, and that was reason enough to consider it. But the shift in perspective had begun. Once a new way of seeing is suggested, it can't easily be unsuggested. The next thinkers to take up Copernicus's vision carried it further, testing it against the sky itself. Among them was Tycho Brahe, a Danish nobleman and astronomer who built one of the first great observatories long before telescopes existed. He recorded the positions of planets and stars with extraordinary precision. His instruments were mechanical, made of brass and wood, yet his measurements were accurate to within a fraction of a degree. Tycho himself favoured a hybrid model, Earth fixed at the centre, with the Sun circling it and the other planets circling the Sun. It was a compromise, halfway between old belief and new evidence. But his meticulous data would later provide the foundation for the next leap forward. That leap came through Johannes Kepler, Tycho's assistant, who inherited his records after his death. Kepler was a mathematician and a mystic, driven by both logic and a sense of cosmic harmony. He believed that geometry was the language of the universe, and that the planets moved according to divine order. When he began studying Tycho's data, he expected to find that order in perfect circles, as everyone else had assumed. What he found instead were deviations, tiny but undeniable. The planets didn't move in circles, they moved in ellipses. It took him years to accept what the evidence demanded. The perfection of circles had been an article of faith since ancient Greece. To replace them with ovals felt almost like sacrilege. But Kepler followed the numbers wherever they led, and in doing so he discovered what we now call the laws of planetary motion. Each planet, he found, moves in an elliptical orbit with the Sun at one focus. The closer a planet is to the Sun, the faster it moves, and the time it takes to complete an orbit relates precisely to its distance. These relationships were not philosophical ideas, they were mathematical facts. Kepler's discovery turned the universe from a static arrangement into a dynamic system. The heavens were no longer perfect and unchanging. They were in motion, alive with predictable rhythm. It was the first time anyone had described the physical laws of planetary movement. What had once been myth and geometry became mechanics. While Kepler was transforming orbits into equations, another man was changing the way we saw the sky itself. Galileo Galilei, armed with one of the earliest telescopes, began to observe the heavens in 1609. His telescope was modest by modern standards, but it revealed things no one had ever seen. He looked at the moon and found mountains and craters. He looked at Jupiter and saw its 4 largest moons circling it. He looked at Venus and discovered that it went through phases like the moon, waxing and waning as it orbited the Sun. That one observation alone was enough to prove the Copernican model. If Venus showed phases, it had to be orbiting the Sun, not the Earth. Galileo published his findings in vivid detail. He wrote not just for scholars, but for anyone willing to look. The simplicity of the evidence was its strength. A telescope and a little patience were enough to see the truth for yourself. That directness was dangerous. It stripped authority from institutions and placed it in the hands of observation. For that, Galileo faced persecution, but his work endured. The worlds he revealed, the rough surface of the moons of Jupiter, the rings of Saturn, expanded the human sense of what was possible. Planets were not divine lights, they were places. Some had their own companions. The cosmos had structure far beyond what anyone had imagined. From Copernicus to Galileo, the idea of worlds took on new meaning. Planets were no longer symbols but physical bodies. They had gravity, mass and motion. Their behaviour could be measured and predicted. By the time Isaac Newton entered the story in the 17th century, the pieces were in place for a unified explanation. Newton's laws of motion and universal gravitation tied it all together. He showed that the same force pulling an apple to the ground kept the moon in orbit around Earth, and the planets in orbit around the sun. Gravity wasn't local or mystical, it was universal. The heavens and the earth were governed by the same rules. That realization ended the ancient separation between celestial and terrestrial. For the first time, the universe was one continuous system. The planets were not perfect spheres on glass tracks, but material worlds moving through space. Earth was just another planet among them. The concept was radical, not because it diminished humanity, but because it connected everything. The same equations that described a falling stone described the paths of worlds. In the centuries that followed, the solar system became a laboratory for discovery. Telescopes grew larger, their lenses clearer. Uranus was discovered in 1781, Neptune in 1846. Each new planet extended the reach of our system, but it also raised a deeper question. Was our sun unique? Were there other stars with their own families of planets? Astronomers suspected it was likely, but they had no way to prove it. The distances were too great, the stars too bright. The dream of other worlds moved once again from certainty back into imagination. Yet even as evidence remained out of reach, the idea became woven into scientific expectation. If gravity and motion were universal, then the processes that formed our solar system should also occur elsewhere. The nebula hypothesis, proposed by Immanuel Kant and later refined by Pierre-Simon Laplace, suggested that stars and planets formed together from spinning clouds of gas and dust. That meant that wherever stars formed, planets should form too. The universe, by its nature, would be full of worlds. That insight brought the story full circle. The early dreamers had imagined other worlds as divine realms. Now science imagined them as natural consequences of physics. The difference was one of language, not of wonder. The cosmos was still a place of endless variety, but its mechanisms were becoming clear. Gravity, motion, and time shaped everything. Worlds took shape not by will but by process. Even so, the imagination of other planets continued to stretch beyond the measurable. In the 19th century, when telescopes grew powerful enough to see the surface of Mars as a disk, observers thought they saw channels, long straight lines crisscrossing the planet. They were optical illusions, but they sparked the idea of Martian civilizations, vast irrigation systems built by intelligent beings. The fantasy spread quickly, showing how deeply the human mind wanted companionship in the stars. The science was wrong, but the longing was real. As technology improved, illusions gave way to clarity. By the mid-20th century, we sent probes to the planets of our own solar system. One by one, they revealed their true nature. The channels on Mars were valleys and shadows. Venus was not a swampy twin of Earth, but a furnace under a thick atmosphere of carbon dioxide. Jupiter and Saturn were colossal gas worlds, beautiful but inhospitable. The more we saw, the more we understood that every world was unique. The process of their formation, gravity pulling dust into clumps, collisions merging them into spheres, was universal, but the results were endlessly varied. When worlds take shape, they follow simple rules, but the outcomes are diverse. The composition of the original cloud, the distance from the forming star, the collisions along the way, All these factors decide whether a world becomes rocky, gaseous, icy, or something stranger. Planets form in chaos and settle into order. Our solar system is the product of billions of years of collisions, rearrangements, and gradual cooling. Every world carries the marks of that history in its craters and layers. The smooth orbits we see today are the quiet aftermath of an ancient storm. That same process is happening throughout the galaxy. Around newborn stars in distant nebulae, disks of dust and gas still spin, glowing faintly in infrared light. Within those disks, particles collide, stick and grow. It's the same story repeated endlessly, the same physics at work on every scale. The birth of planets is not a rare event, it's part of the life cycle of stars. To form a star is to form a system. The light that reaches us from distant stellar nurseries carries with it the promise of new worlds being born. By the time the first exoplanet was confirmed in the 1990s, the idea had been waiting for proof for centuries. The groundwork laid by Copernicus, Kepler, Galileo and Newton had long suggested that the universe must be filled with planets. What we lacked was the evidence. When it finally arrived, it wasn't a surprise. It was a confirmation of something we had suspected all along. That planet formation is a natural part of the cosmos. From the earliest theories of spinning clouds to the modern simulations run on supercomputers, the story remains the same. Worlds take shape because the universe allows no idle dust. Gravity gathers, motion organizes, and time sculpts. Each planet, large or small, is a record of those three forces working together. The Earth itself is one such record, a world that cooled, settled, and eventually grew life on its surface. In that sense, we are the continuation of the same process that began in the swirling dust around a young sun. When we speak of worlds taking shape, we're also speaking about ourselves. The same materials, the same physics, the same cosmic history bind everything together. Every new planet discovered elsewhere is a reminder that the processes that made us are still happening everywhere. The early dreamers couldn't have known it, but their question, "What are these wandering lights?" was the first step toward understanding our own origins. The journey from myth to mechanism, from imagination to measurement, transformed not only astronomy, but humanity's place in the cosmos. The planets were no longer gods but siblings, formed from the same dust, governed by the same rules. That realization didn't make the universe smaller. It made it infinite in a new way. The more we understood how worlds formed, the more we could see that the sky above was not an unreachable ceiling, but a living landscape, full of motion and change. And still, even with all we've learned, that landscape remains full of mystery. Beyond the reach of our instruments, more worlds are forming even now. Dust clouds collapse, disks spin, and new systems begin their long orbits. The galaxy is never still. It continues to build itself, one planet at a time. We're part of that same movement, travelling within it, looking outward from one of its countless homes. The story of when worlds took shape is not only about the past, it's still happening. It always will be. For a long time, our solar system felt like the edge of everything. Once telescopes showed us its structure in full, with planets moving predictably around the sun, it seemed complete. There was the central light, its family of worlds, and beyond them, only darkness. Even as astronomy advanced, the idea that other systems might exist remained a quiet speculation. We had learned that Earth was not the centre, that the sun was just another star, but our reach ended there. The planets we could see and measure became the limits of our world, the known horizon of space. Beyond that horizon, the universe stretched outward, full of stars but without evidence of anything else. The 19th century was a period of immense confidence in science. Newton's laws described the mechanics of the heavens with astonishing precision. The orbits of planets could be predicted centuries in advance. The discovery of Neptune, inferred from mathematical irregularities in Uranus's motion, confirmed that prediction and deepened faith in the order of nature. If unseen planets could be found within our system by calculation alone, it seemed natural to imagine that other stars might have their own invisible companions. Yet it was still imagination. The stars remained points of light, too far for their details to be known. Astronomers could split their light into spectra, study their chemical compositions, estimate their distances, but the space around them stayed blank. The dream of other solar systems persisted without proof. That dream took many shapes. Some writers, like Camille Flammarion in the late 1800s, wrote with poetic certainty that the universe was full of inhabited worlds. Others speculated with more restraint, suggesting that planetary systems might be rare, or that our own might be unusual. No one could say for sure. The instruments were not yet capable of resolving the truth. The light from a distant star overwhelmed everything around it, hiding any smaller bodies in its glare. Even the nearest star, Proxima Centauri, was too far for planets to be seen by any direct means. The early 20th century brought new methods of observation. Photography replaced sketching at the telescope's eyepiece. Spectroscopy became more precise. Theories of star formation improved. Astronomers began to understand that stars were born from collapsing clouds of gas and dust. In those swirling clouds, rotation would naturally create a disk around the forming star. That disk, as the nebula hypothesis had predicted, could give rise to planets. It was a simple extrapolation to assume that the process was universal. If every star formed this way, then every star should have a disk, and every disk should, in time, produce worlds. Even so, proving it remained beyond reach. The distances were enormous, the light faint. Telescopes could reveal galaxies and nebula, but not the small companions of single stars. For decades, astronomy had to live with the tension between certainty in theory and ignorance in evidence. The assumption of other planets became part of scientific common sense, but the proof was absent. The idea lived in books, equations, and speculation, not in observation. During the mid-20th century, as spaceflight became possible, the perspective shifted again. The first photographs of Earth from orbit changed how humanity saw itself. The blue sphere suspended in darkness was both familiar and new. For the first time, our world could be seen as a planet, not as the centre of anything, but as one among many. Probes sent to other planets in our solar system showed landscapes that were alien yet comprehensible. Valleys on Mars, clouds on Venus, storms on Jupiter. These worlds were real places, physical and diverse. They transformed the imagination of what might exist beyond. The idea of planets around other stars began to feel less like fantasy and more like inevitability. If the same physical laws applied everywhere, then there was no reason for planetary formation to be limited to our Sun. Still, the challenge of detection remained. Astronomers developed instruments sensitive enough to measure the tiny motions of stars, hoping to find the telltale signs of gravitational influence from unseen companions. They knew that a planet orbiting a star would cause the star to move slightly, wobbling around a shared centre of mass. The movement would be small, perhaps only a few meters per second, but measurable if the instruments were stable enough. Detecting such subtle shifts required patience, precision, and time. While astronomers refined their instruments, the broader culture was already imagining what might lie beyond. Science fiction filled the gap that evidence had not yet closed. Stories of other worlds, some barren, some alive, some inhabited by civilizations beyond comprehension, became part of collective thought. Those stories were not evidence, but they kept curiosity alive. They gave the idea emotional weight. When technology eventually caught up, the discoveries that followed felt like the fulfillment of promises made by imagination. By the 1980s, small signs began to appear. There were hints of irregularities in the light of certain stars, slight variations that might indicate orbiting companions. Some detections were later disproven, others remained unconfirmed. The difficulty lay in distinguishing the motion caused by planets from the natural fluctuations of the stars themselves. Many early claims of planet discoveries faded under scrutiny. The dream of other worlds seemed close enough to touch, yet always just out of reach. Then, in 1992, the first confirmed detection arrived, and it came from an unexpected place. Astronomers Alexander Volschan and Dale Frail, using the Arecibo radio telescope, detected tiny timing variations in the pulses of a neutron star, a pulsar known as PSR 57 pulsars. Pulsars emit regular radio signals, spinning like lighthouses in space. The slight irregularities in those pulses indicated that something was tugging on the star. The only possible explanation was the presence of planets. The discovery was strange and poetic. The first known exoplanets were orbiting a dead star, the remnant of a supernova. They were unlike anything imagined before, planets surviving the death of their sun, circling a corpse of unimaginable density. That discovery broke the silence. It proved that planets existed elsewhere, even in extreme environments. But astronomers wanted to find them around normal stars, around suns like our own. That confirmation came only a few years later. In 1995, Michel Mayor and Didier Queloz announced the discovery of a planet orbiting the star 51 Pegasi. The planet was massive, about half the size of Jupiter, and it orbited extremely close to its star, so close that its year lasted only 4 Earth days. It was unlike any planet in our solar system, a giant world baking in starlight. Its existence challenged assumptions about how planetary systems formed, but it confirmed what many had long believed. Other stars have planets. Once the first discovery was made, others followed quickly. Astronomers developed 2 main methods for detection. The first, called the radial velocity method, measured the wobble of a star caused by the gravitational pull of its planet. The second, called the transit method, looked for the tiny dip in a star's brightness that occurs when a planet passes in front of it. These techniques, refined with better instruments and longer observation times, began to reveal a galaxy filled with planets of every kind. Each detection added another piece to the growing picture of the Milky Way as a system full of planetary families. The first exoplanets found were mostly large and close to their stars, so-called hot Jupiters, because they were easiest to detect. But as sensitivity improved, smaller and more distant planets began to appear in the data. Some were rocky like Earth, others gaseous like Neptune, others entirely different from anything we knew. The diversity was greater than anyone had expected. Beyond the solar shores, the universe was busy. Planets were not rare jewels scattered through emptiness. They were common, natural byproducts of star formation. The Milky Way, once thought to be a collection of stars alone, revealed itself as a galaxy of worlds. By the early 2000s, hundreds of exoplanets had been confirmed. By the 2010s, the number had reached thousands. Each one represented a system, a history, a process of formation and survival. Some orbit binary stars where 2 suns rise and set together. Some circle red dwarfs, faint and cool but long-lived. Some drift alone, having been ejected from their systems to wander the dark between stars. The phrase beyond the solar shores no longer meant unreachable mystery. It became a frontier of study. Space telescopes like Kepler and TESS dedicated themselves to searching for transits across thousands of stars. They found patterns where before there was only speculation. Whole catalogues of worlds emerged, some similar to our own, many completely alien. The variety defied easy classification. There were planets with orbits so tight that their surfaces glowed with heat, and others so distant that they were frozen in perpetual night. There were super-Earths, mini-Neptunes, and worlds where the atmosphere might rain iron or methane. The galaxy's imagination seemed boundless. As more data came in, astronomers began to estimate the total number of planets in the Milky Way. Even conservative models suggested at least 1 planet per star. Since the galaxy contains roughly 400 billion stars, that means there are at least 400 billion planets, and possibly far more. Many of those systems likely have multiple planets, just as ours does. That would push the number into the trillions. The scale is almost impossible to internalize, yet each of those distant worlds, no matter how strange or unreachable, is real. They orbit suns we can see through telescopes, suns whose light takes years to reach us. Every faint star that glimmers in the night sky may have its own collection of planets, some scorched, some frozen, some temperate. The distances make them unreachable for now, but knowing they exist changes the nature of the night. The sky becomes a landscape, not an abstraction. Every point of light is a system, every patch of darkness filled with invisible orbits. The discovery of exoplanets did more than expand astronomy. It reshaped how we understand our own place. It showed that our solar system is not a special arrangement, but one version of a universal pattern. The processes that formed Earth, Mars, and Jupiter are happening everywhere. Planet formation is not a rare accident, but a regular feature of cosmic evolution. In that sense, the universe is not sparse, but fertile. The same laws that sculpted our system are at work across the galaxy, shaping worlds in every direction. As our instruments improved, astronomers began to study exoplanet atmospheres. By analysing the light passing through them during transits, they could identify chemical signatures: hydrogen, oxygen, methane, water vapour. Each new detection brought the search closer to the question that underlies all of this: whether life exists elsewhere. The evidence is still indirect, the data limited, but the possibility feels more tangible than ever. The discovery of planets beyond the solar shores turned that question from speculation into something measurable. Beyond those measurements lies a deeper realization. The galaxy is not static. It is dynamic and ongoing. Stars are still forming in clouds of dust. New systems are still being born. The count of planets is not fixed. It increases with time, as each new star brings with it a new collection of worlds. The Milky Way is a continuous process, a living structure of creation and motion. When we look outward, we're not looking at a completed picture, but at something still unfolding. The distance between our small solar system and those distant worlds is immense, yet in understanding them, we come closer to understanding ourselves. Every exoplanet discovered tells us something about the possibilities of matter and motion, about how stable or chaotic systems can be, about the limits of habitability and the extremes of survival. Together they form a map of what the universe can make. That map is still incomplete, but it grows every year, line by line, orbit by orbit. The story of discovery is far from finished. New instruments, both on the ground and in orbit, continue to refine what we can detect. Telescopes, like the James Webb Space Telescope, peer into the infrared, studying the faint warmth of distant planets. Future missions will aim to directly image Earth-like worlds around nearby stars, separating their light from their suns. What was once imagination now guides engineering. Each improvement brings more of the invisible into view. Beyond the solar shores, the galaxy stretches without end. Its spiral arms, filled with gas, dust and light, hold the ongoing story of creation. In every direction, planets circle stars in endless motion. Some may be lifeless rocks, others vibrant with chemistry we haven't yet imagined. We may never visit most of them, but knowing they exist fills the darkness with meaning. The universe is not a void. It is a vast continuum of worlds, each born from the same processes, each following the same rules, each a quiet echo of the same origin. And as our instruments watch the stars flicker, measuring each subtle change, we continue to listen to the galaxy's rhythm. Every tiny dimming of starlight could be a planet passing by, another confirmation that the pattern continues. The discovery never really ends. There will always be more beyond what we can see. The solar shores we once thought of as boundaries are now only beginnings, and everything beyond them is waiting to be found. The idea that other worlds existed had lingered at the edge of science for centuries, quiet but persistent. waiting for proof. By the late 20th century, astronomers had grown almost certain that planets must circle other stars. The evidence of how stars formed, the structure of our own system, and the uniformity of physical laws all pointed toward that conclusion. Yet for all the confidence in theory, there remained a hollow space where data should have been. No one had yet seen the unmistakable signs of another world. The sky was still officially full of stars and nothing more. Then, without warning, the proof arrived from an unexpected corner of the cosmos. It didn't come from a nearby star or a system like our own. It came from the husk of a dead sun, a place of unimaginable violence and precision. In 1992, Alexander Folstjan and Dale Frail announced the discovery of planets orbiting a pulsar, a neutron star left behind after a supernova explosion. It was a strange and haunting setting for the first confirmed exoplanets, but there they were, invisible yet unmistakable in their effect. The discovery rewrote the expectations of where planets could exist and what forms survival could take. The pulsar in question, known as PSR B1257-12, sits roughly 2,000 light-years away in the constellation Virgo. A pulsar is the remnant of a massive star that has collapsed under its own gravity after exhausting its fuel. What remains is a sphere only a few kilometers wide, but so dense that a single teaspoon of its material would weigh billions of tons. It spins rapidly, sending out beams of radio waves that sweep across space like the light of a cosmic lighthouse. Those pulses are regular with astonishing precision, often more stable than atomic clocks. Any slight deviation in their timing can be measured and traced to external influences. Volstjan and Frail were studying these pulses when they noticed something peculiar. The arrival times of the radio signals weren't perfectly regular. They varied slightly, as though the pulsar were being tugged back and forth by something unseen. The only plausible explanation was gravitational. Small bodies orbiting the pulsar were disturbing its motion. By analysing those variations, they determined the masses and orbits of the objects responsible. They found 2 planets, each several times more massive than Earth, orbiting at distances comparable to those of Mercury and Venus. Later, a third smaller planet was identified. It was an extraordinary result. These were not planets in any ordinary sense. They were circling a corpse of a star, in a region once blasted by a supernova explosion. Somehow, after that cataclysm, solid bodies had either survived or formed anew from the remnants. The existence of such planets showed that the process of planet formation, or reformation, was more resilient than anyone had believed. It meant that even in the most extreme environments, gravity could gather matter into stable worlds. The discovery was met with cautious excitement. Many astronomers were amazed but puzzled. Planets around pulsars were an unexpected starting point. They proved the principle that planets could exist beyond the solar system, but raised new questions about how they came to be. Theorists proposed that after the supernova, a disk of material might have formed around the pulsar, and from that disk new planets condensed. Others suggested that the planets were survivors from before the explosion, somehow enduring its violence. Whatever the mechanism, the result was undeniable. The first confirmed exoplanets existed, and the universe suddenly felt fuller. For the first time in human history, the existence of planets beyond our sun was not a matter of faith, philosophy, or speculation. It was a matter of measurement. The announcement marked a shift from centuries of imagining to an era of discovery. Yet the find was so unusual that many still longed for confirmation around a normal star. A pulsar system was proof, but it was an odd, extreme proof, not the quiet confirmation that might settle the imagination. That would come soon enough. In 1995, Michel Mayor and Didier Queloz, working at the University of Geneva, published their detection of a planet orbiting the Sun-like star 51 Pegasi. It was the first confirmed exoplanet around a main sequence star, and its discovery changed astronomy permanently. The planet, known as 51 Pegasi b, was nothing like the worlds in our solar system. It was about half the mass of Jupiter, but it orbited its star at a distance closer than Mercury orbits the Sun. Its year lasted only 4 Earth days. The discovery was made using the radial velocity method, which measures the small Doppler shift in a star's light as it moves toward and away from us due to the gravitational pull of an orbiting planet. The precision required was astonishing. The motion of 51 pegasi caused its spectral lines to shift by only a few meters per second, yet that was enough for Mayer and Queloz to detect. The signal repeated regularly, every 4.2 days, revealing the presence of a companion. When they first saw the pattern, they were skeptical. No one had expected such a massive planet to orbit so close to its star. Theoretical models suggested that gas giants should form far from their suns, where temperatures are low enough for hydrogen and helium to condense. Yet here was a Jupiter-sized planet hugging its star so tightly that its atmosphere must have been blistered by heat. The existence of 51 Pegasi b forced a re-evaluation of planetary formation theories. It introduced a new class of exoplanets, soon dubbed hot Jupiters. These were giant worlds with short orbital periods, common enough to be detected easily with available instruments. Their discovery showed that planetary systems could form in far more diverse configurations than our own. The solar system, once thought to represent a typical pattern, was revealed to be only one possibility among many. The impact of that first detection rippled through the scientific community. Within months, other teams began reanalyzing their data, looking for similar patterns. More hot Jupiters were found. Each new discovery reinforced the conclusion that planets were common and diverse. The age of speculation was over. The age of cataloguing had begun. What made these discoveries so transformative was not just what they revealed about other systems, but what they implied about the galaxy itself. If our instruments, limited as they were, could find planets around nearby stars with relative ease, then planets must be abundant. The night sky, once imagined as a field of solitary suns, was now known to be filled with families of worlds. Each star could be a centre of its own miniature cosmos, with orbits and climates and histories as rich and varied as our own. After 51 Pegasi b, the rate of discovery accelerated. New instruments were designed specifically for precision radial velocity measurements. The Corrali spectrograph, installed at the La Silla Observatory in Chile, began identifying more planets with short orbital periods. The discoveries multiplied until they could no longer be considered rare. Their pattern became unmistakable. Planets are everywhere. Each detection brought a sense of perspective. The universe, long perceived as vast but mostly empty, became an ocean of orbits. The early detections were the first ripples on the surface of a realization that would deepen with every passing year. By the early 2000s, hundreds of exoplanets had been identified. The discoveries revealed new categories of planets, super-Earths, mini-Neptunes, and others without analogues in our solar system. The variety of orbital configurations defied prediction. Some systems contained planets packed closely together, circling their star in tight resonant chains. Others contained distant giants with elongated eccentric orbits. The neat arrangement of our own solar system turned out to be only one of many possible architectures. The first exoplanet discoveries also changed how scientists thought about habitability. For generations, the search for life beyond Earth had been limited by imagination. People pictured other Earths orbiting other suns, with climates and conditions similar to ours. The early detections broadened that picture. They showed that nature produces planets under a vast range of conditions, many of which are far from what we consider comfortable. Life, if it exists elsewhere, might thrive in forms and environments that we cannot easily imagine. The pulsar planets and 51 Pegasi b together mark the true beginning of exoplanetary science. One showed that planets could exist in the most hostile environments imaginable. The other showed that they existed around stars like our Sun. Between them lay the full range of possibility. They demonstrated that planetary formation was not fragile or limited, but resilient and prolific. Gravity, given enough time and material, would build worlds wherever it could. In the years that followed, the methods of detection became more refined. The transit method, which measures the dimming of a star's light as a planet passes in front of it, opened a new window of precision. It allowed astronomers not only to confirm the existence of planets, but to measure their sizes, densities, and even atmospheric compositions. When the Kepler Space Telescope was launched in 2009, it carried that method into orbit, free from the distortions of Earth's atmosphere. It watched a single patch of sky for years, observing the light of more than 150,000 stars. Every time a star dimmed by a tiny fraction and then brightened again in a consistent rhythm, it revealed the presence of a planet. The data Kepler returned transformed our understanding of the galaxy. In its 4 years of operation, it identified thousands of exoplanets, including many smaller Earth-sized ones. It confirmed statistically what the early detections had implied. Planets are not rare exceptions but standard features of stars. The first exoplanet discovery in 1992 had been a surprise. 2 decades later, the surprise was how many there were. Looking back, the first exoplanet detections seem almost humble compared to what followed, but they carry the weight of transformation. They mark the moment when humanity crossed a threshold in knowledge, from isolation to abundance. Before them, the solar system felt like an island. After them, it became one archipelago among billions. The proof that planets existed elsewhere changed not only astronomy, but the collective imagination of what the universe is. It shifted the human narrative from uniqueness to participation. The pulsar planets remain an oddity, a reminder that the universe allows for outcomes beyond our expectations. They orbit their collapsed star with unbroken regularity, continuing their silent revolutions around something that long ago burned itself out. 51 Pegasi b, the first planet found around a star like our Sun, continues to circle its host at blistering speed, completing each orbit in less than a week. These first worlds are distant, unreachable, but they stand as markers of a turning point in understanding. They were the threshold, the moment the invisible became measurable. Every discovery since then has built upon that foundation. The catalogue of known exoplanets grows each year, now numbering in the thousands. The diversity of their forms continues to expand, revealing a galaxy that is not static but endlessly inventive. What began as a question, do other worlds exist, has become a field of study with more data than imagination once dared to supply. The first exoplanet discoveries are no longer isolated moments in history. They are the roots of an ongoing exploration that continues to redefine the scale of our understanding. From pulsars to hot Jupiters, from the edge of detection to the vast catalogues of modern surveys, the story stretches forward without end. The first exoplanet was not an answer. It was an opening. It turned a silent sky into a populated one, a flat map into a living landscape. Beyond those first detections, the pattern continues, extending through space and time, each new world adding to the quiet chorus of motion that fills the galaxy. And so, from the first exoplanet to the next, the discovery has never been about endings. It has always been about continuation. The same physics that shapes the orbits of those distant worlds shapes ours. The same forces that gathered their dust gathered ours. The same light that warms their skies shines here. The first exoplanet was a beginning, but the story it started still unfolds with every observation, every measurement, and every realization that the universe is more full, more complex, and more familiar than we ever thought. The discoveries that followed the first exoplanets were not made through sight in any ordinary sense. No telescope ever captured a clear image of those distant worlds. They were not seen, but inferred. Their presence revealed itself only through the smallest changes in light and motion, in signals that seemed too faint to carry meaning yet contained entire planetary systems hidden within them. Finding the invisible became an art of precision, a conversation between light and mathematics. Each method that astronomers developed was a new way of listening to the cosmos to detect patterns too subtle for the human eye. The most fundamental principle behind every discovery is simple. Planets and stars are bound together by gravity, and that bond leaves traces. A planet does not orbit its star alone while the star remains still. Both bodies move, circling a common centre of mass. The star's motion is tiny compared to the planet's, but it exists, a slow rhythm of approach and retreat. To detect that motion, astronomers measure the star's light in extraordinary detail, searching for the small shifts caused by the Doppler effect. When the star moves toward us, its light compresses slightly, shifting toward the blue end of the spectrum. When it moves away, the light stretches, shifting toward red. The changes are minute, sometimes only a few meters per second, but they can be recorded. This method, known as the radial velocity technique, was the one that revealed 51 Pegasi b in 1995. It remains one of the most effective tools for detecting planets, especially large ones close to their stars. Each measurement produces a curve, a repeating pattern of motion over time. From that curve, astronomers can deduce the planet's orbital period, its minimum mass, and the shape of its orbit. The process is meticulous. Observations must be made for months or years, accounting for every possible interference, from the movement of the observatory itself to the faint pulsations within the star. Yet the reward is profound. A single, repeating signal, consistent across years, is enough to confirm that a planet is there. The radial velocity method works best for stars whose light is steady and sharp, where spectral lines can be measured without distortion. For others, a different approach is needed. The transit method, now famous for its precision, measures not the motion of the star but the small dimming of its light as a planet passes in front of it. When a planet crosses the face of its star as seen from Earth, it blocks a tiny fraction of the starlight. The drop in brightness can be less than 1%, sometimes even a few thousandths, but modern instruments can detect it. Each dip in light, if it repeats with regular timing, marks the orbit of a planet. The beauty of the transit method lies in its simplicity and its power. By measuring the depth and duration of the dip, astronomers can determine the planet's size relative to the star. When combined with radial velocity measurements, which provide mass, the two methods together reveal density, composition, and even atmosphere. In this way, worlds that cannot be seen directly become tangible objects with measurable characteristics. The invisible becomes defined by the faintest fluctuations in light. The precision required for such work is extraordinary. Instruments must detect changes in brightness, equivalent to the difference between a lighthouse shining at full intensity and then dimming by the flicker of a candle. The Kepler Space Telescope was built for exactly that purpose. Launched in 2009, it observed a single region of the sky continuously, measuring the light from more than 100,000 stars. Over the years, it recorded thousands of tiny dips in brightness. Each one was a whisper of motion, a sign of an orbiting planet. Kepler's observations transformed astronomy. It showed that planets were not the rare exceptions once imagined, but the rule. Every few days, another light curve revealed another world. The spacecraft detected systems with multiple planets, some with tight, synchronized orbits, others with wide separations. By the end of its mission, Kepler had confirmed thousands of exoplanets and suggested that the Milky Way likely contains more planets than stars. While Kepler watched for transits, ground-based observatories continued to refine radial velocity techniques. New instruments like HARPS in Chile and HIRES in Hawaii achieved precisions once thought impossible. They measured stellar motions of just a few centimeters per second. Such sensitivity opened the door to detecting smaller planets, those closer in size to Earth. The faint signatures of super-Earths began to appear, revealing that small rocky worlds are at least as common as gas giants. Yet even these precise techniques reveal only a fraction of what exists. Most planetary systems are oriented in ways that make transits invisible from our perspective. We can detect only those whose orbits line up by chance with our line of sight. Others must be found by indirect means. One such method, astrometry, measures the position of a star in the sky with exquisite accuracy. If a planet is orbiting it, the star's position will trace a tiny cyclic path over time. The motion is so slight that only the most stable instruments can detect it, but when measured it provides a direct estimate of the planet's mass and orbit. The Gaia spacecraft, launched by the European Space Agency, is now performing this work, mapping the positions of over 1 billion stars with unprecedented precision. Its data will reveal planets through their subtle gravitational tugs, adding yet another layer to the map of invisible worlds. Another approach relies on the bending of light itself. When a massive object passes in front of a more distant star, its gravity acts like a lens, magnifying the background light. This phenomenon, known as gravitational microlensing, can reveal the presence of planets around the lensing star. The event is brief and cannot be repeated, but it provides information about planets at great distances, including those that orbit faint or distant stars not detectable by other means. In this way, planets are discovered not through continuous observation, but through rare alignments, brief flashes of evidence caught by chance. Each of these methods, whether measuring light, motion, or gravity, relies on patterns rather than images. Planets remain invisible, but their effects are unmistakable. The data collected from them require careful interpretation. Signals can be corrupted by stellar activity, instrumental noise, or the motion of the observatory itself. Every candidate planet must be verified through multiple checks before it is confirmed. The process can take years, but patience is built into the nature of astronomy. Time, after all, is one of its primary tools. Even with the best instruments, the direct imaging of exoplanets remains rare. The glare of a star overwhelms the faint light reflected by its planets, often by factors of billions. To overcome this, astronomers use techniques like coronagraphy, which blocks the star's light so the space around it can be studied. With this method, large planets orbiting far from their stars can sometimes be seen directly. The images are not detailed, just faint points of light near brighter ones, but they are real photons reflected from alien worlds. Each one represents an immense technical triumph, a moment where the invisible becomes visible for the first time. Infrared astronomy adds another dimension. Planets, especially young ones, emit infrared radiation from the heat of their formation. Instruments sensitive to those wavelengths can detect their glow, distinguishing them from the cooler background of space. The James Webb Space Telescope, launched decades after the first exoplanet discoveries, carries the most advanced infrared instruments yet. It can separate the light of a planet from its star and analyze it to detect atmospheric components. With such tools, astronomers have begun to identify molecules like water vapor, carbon dioxide, and methane in exoplanet atmospheres. Each detection is another step toward understanding what these distant worlds are made of. Behind every discovery lies an immense infrastructure of data, calibration, and interpretation. Telescopes collect light, instruments translate it into numbers, and those numbers become graphs and curves. The curves become evidence, and the evidence becomes confirmation. The process is long, meticulous, and often quiet. There are no dramatic visuals, no sudden revelations, just slow accumulation of certainty. Astronomy moves at the pace of the universe it studies. Finding the invisible also depends on collaboration. Observatories around the world coordinate observations, confirming each other's detections and combining data. Amateur astronomers sometimes contribute by monitoring known transit candidates, adding to the continuous record. Each detection, no matter how distant, is the product of a network of minds and machines, united by a shared goal: to turn faint light into understanding. As the methods improve, new categories of planets come into focus. Some are smaller than Mercury, others larger than Jupiter. Some orbit their stars so closely that they complete an orbit in less than a day, while others drift so far that their years last centuries. There are planets with atmospheres of hydrogen and helium, others rich in carbon or sulfur. Some have densities suggesting oceans beneath ice, others so massive that their gravity crushes any concept of surface. The diversity is vast, but the detection methods treat them all the same, as patterns in light, measurable and real. The phrase, "finding the invisible," might sound poetic, but it is literal. These worlds do not reflect enough light to be seen by human eyes, yet the traces they leave are quantifiable, their presence undeniable. They tilt their stars, dim their light, shift their spectra, and bend the path of photons across space. In those distortions, the shape of the galaxy emerges. The invisible, multiplied by billions, becomes the structure of everything. Even as technology advances, the fundamental act remains the same: watching, recording, and waiting. The methods may vary, but the essence of discovery lies in patience. Light travels across years of space to reach the sensors that measure it. Every photon carries the history of its journey. To detect a planet is to intercept that history and read it. It is a slow conversation with the universe, spoken in wavelengths and time. The next generation of instruments will refine this conversation further. Planned missions aim to detect Earth-sized planets in habitable zones around nearby stars. These planets, small and faint, require precision beyond what even Kepler could achieve. New techniques, like starshade missions that block a star's light with an orbiting screen, promise direct imaging of worlds like ours. The data will not only confirm their existence, but allow study of their atmospheres in search of chemical signs of life. Yet even as the tools grow more complex, the sense of wonder remains simple. Every detection, every curve in a light graph is a connection across space and time. Each one tells us that the universe is not silent, that motion and matter continue their endless interplay in places far beyond our reach. The planets we find are distant, but their presence brings the galaxy closer, turning abstraction into evidence. Finding the invisible has reshaped what astronomy means. It is no longer limited to what can be seen through glass, but extends into what can be inferred through data. The boundary between visible and invisible is blurred, replaced by a continuum of understanding. The universe, once thought to be made mostly of stars, now reveals itself as a tapestry of worlds. The faint signals continue to arrive, one after another. Each one is a small deflection in light, a brief whisper of movement, a mathematical rhythm repeating across time. From those signals we build a picture of what exists beyond our solar shores. The invisible becomes a map, and the map becomes a reflection of how much more there is to learn. And through that patient search, the galaxy slowly comes into focus, not through images of planets themselves, but through the patterns that reveal them. In those patterns lies the truth that the universe does not hide its abundance. It only waits for eyes steady enough and instruments quiet enough to notice. The work of finding planets had begun on the ground, in observatories scattered across mountains and deserts, where astronomers pointed their instruments toward individual stars, watching for the faint tremors that betrayed unseen companions. It was deliberate and slow, each discovery requiring months or years of patient measurement. By the time the first few hundred exoplanets had been confirmed, the evidence was undeniable, yet the view was incomplete. The methods worked well, but they reached only as far as the sky's randomness allowed. Each detection depended on alignment, on chance, on a single star behaving just so. The discoveries, though profound, were scattered like isolated dots on a map with vast blank spaces in between. The next step would require something larger, something capable of turning a fragmentary understanding into a picture of the whole. That step came in the form of a telescope that didn't look out across the entire sky. but instead focused on one small patch of it, staring unblinkingly for years. Its name was Kepler. Launched by NASA in 2009, the Kepler Space Telescope was designed for a singular purpose: to measure the light of thousands of stars simultaneously and continuously, looking for the subtle, periodic dimming that indicated a planet passing in front of its host. Its field of view was small, only a fraction of the sky, but within that narrow window lay over 100,000 stars, each a potential home to planets waiting to be found. Kepler's task was simple in concept but immense in execution. It had to detect changes in brightness as small as 1 part in 10,000, distinguishing them from noise, from instrumental fluctuations, and from the star's own natural variability. It was not designed to image planets directly or to capture dramatic photographs. Instead, it produced light curves, graphs of brightness over time, lines that rose and fell with subtle rhythm. The telescope's instruments converted those variations into streams of data, transmitted back to Earth for analysis. From those small changes, astronomers could infer the existence, size, and orbit of planets, too distant and dim to ever see. When Kepler began its observations, expectations were cautious. Astronomers hoped it might find a few hundred planets, perhaps a handful roughly Earth-sized, and maybe 1 or 2 in what they called the habitable zone, the region around a star where temperatures might allow liquid water to exist. But within months of its launch, the telescope began returning results that defied those modest hopes. The first datasets revealed dozens of transit signals, then hundreds. Each signal represented a star dimming with regular precision, the light fading and returning in a pattern that only an orbiting planet could explain. The numbers grew rapidly. By the end of its first year, Kepler had identified thousands of candidate planets. Many were smaller than Jupiter, some smaller even than Earth. There were systems with multiple planets orbiting in close resonance, where their mutual gravity shaped their motions like dancers keeping time to the same music. Others showed worlds circling red dwarf stars, where orbits lasted only a few days but remained stable for billions of years. The telescope's data revealed a galaxy far more crowded and dynamic than anyone had imagined. One of Kepler's most striking revelations was statistical. By observing so many stars at once, it could determine how common planets were, not just around specific stars but across the galaxy as a whole. The answer changed astronomy. The data showed that planets are not rare exceptions but standard outcomes of star formation. On average, every star in the Milky Way hosts at least 1 planet, and many host several. The implication was staggering. With hundreds of billions of stars in the galaxy, there must be hundreds of billions of planets, and perhaps more. The night sky was no longer a collection of solitary suns. It was an ocean of systems, each with its own architecture, its own history, its own potential for life. The Kepler mission not only expanded the count of known worlds, but also revealed their diversity. Before its launch, astronomers expected other systems to resemble ours: small rocky planets near the star, gas giants farther out. Instead, Kepler found arrangements that defied those expectations. There were planets larger than Earth but smaller than Neptune, a size class unknown in our own system but common elsewhere. Some planets orbited so close to their stars that their atmospheres likely boiled away, while others circled in distant, elongated paths. The idea of a typical planetary system disappeared. There was no single pattern, no universal template. The galaxy's creativity was infinite. Among Kepler's discoveries were worlds that stirred something deeper than scientific curiosity. Planets like Kepler 22b, larger than Earth and within its star's habitable zone, became symbols of possibility. It was the first planet confirmed to orbit in a region where liquid water could exist on its surface, and though no one knew what that surface was like, the mere fact of its existence carried weight. It represented the first tangible candidate for a world that might, in some way, resemble home. Many others followed: Kepler 186f, Kepler 452b, and hundreds more, each with parameters suggesting conditions that could, under the right circumstances, allow for life. The data Kepler produced was immense. Each month, the telescope transmitted tens of gigabytes of information back to Earth, light curves for more than 150,000 stars. Teams of scientists around the world worked to identify which variations were caused by planets and which were caused by other phenomena. False positives had to be ruled out. Stars sometimes flickered because of sunspots, flares, or binary companions. Planets revealed themselves only through repeated regular dimming. It was patient, painstaking work, requiring both automation and human intuition. Algorithms processed the bulk of the data, but many discoveries were confirmed by careful eyes, scanning patterns that machines might overlook. The precision of Kepler's measurements allowed for an entirely new kind of statistical astronomy. Instead of counting individual worlds one by one, scientists could estimate the overall distribution of planets in the galaxy. They could determine how common small rocky planets were, how often they occurred in habitable zones, and what fraction of stars hosted multiple planets. These numbers gave weight to what had long been only speculation. The conclusion was simple and profound. Planets are not just common, they are ubiquitous. Nearly every star in the night sky is likely accompanied by one or more planets. For all its power, Kepler was also fragile. In 2013, 4 years into its mission, one of its reaction wheels, part of the system that kept it stable, failed. Then another followed. Without the ability to point precisely, the telescope could no longer continue its primary mission. Engineers, however, found a way to give it a second life. By balancing the spacecraft against the pressure of sunlight, they stabilized it along a new line of sight. The mission continued under a new name, K2, observing different regions of the sky in shorter campaigns. Though less stable, it continued to find planets, adding hundreds more to its catalogue. By the time Kepler's mission ended in 2018, it had observed over 500,000 stars and discovered more than 2,600 confirmed exoplanets, with thousands more candidates awaiting verification. Its data formed the foundation of modern exoplanet science, shaping everything that followed. Each detection added a small piece to the picture of the galaxy's structure, and together they revealed a reality more populated and diverse than anyone had imagined. The Kepler awakening was not just about numbers, it was about perspective. Before Kepler, humanity knew of a few hundred planets beyond the solar system. After Kepler, the count rose into the thousands. But more importantly, the statistics implied billions more. The galaxy was no longer a speculative stage for stories of distant worlds. It was a measurable physical landscape filled with them. The night sky, once seen as a void between stars, became a structure woven from orbits. The telescope's legacy also transformed how scientists think about planetary formation. Kepler's data showed that planets form efficiently and quickly, even around small, faint stars. It revealed that tightly packed systems are common, where multiple planets orbit close to their host stars, sometimes all within a region smaller than Mercury's orbit. It showed that migration, the movement of planets after formation, is a major factor in shaping systems. Hot Jupiters, once thought anomalies, became examples of a process that occurs frequently, where giant planets form far from their stars and then spiral inward over time. Theories of planet formation and dynamics evolved rapidly to match the data, blending observation and simulation into a more complete understanding of how worlds come to be. Kepler's influence extended beyond science into culture. The idea of a galaxy filled with planets entered public consciousness. Artists, writers, and thinkers drew inspiration from the discoveries. Each newly announced world carried a name, a set of numbers, radius, orbital period, temperature. But behind those numbers lay imagination. Every planet was a place that existed. even if we would never see it. Some were likely scorched deserts, others gas giants with roaring winds, but among them were worlds where starlight fell at just the right distance, where temperatures allowed for water, where conditions might have found a fragile balance. As Kepler's mission drew to a close, its data continued to yield discoveries. The archive remains active, with researchers still uncovering new planets years after the telescope fell silent. The patterns it recorded are deep enough to sustain analysis for decades. Its measurements of stellar brightness have also informed studies of stellar activity, variability and evolution, making its legacy broader than even its designers intended. In the years that followed, other missions took up where Kepler left off. The Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, began a broader survey of the sky, focusing on nearby bright stars. Its discoveries build directly on Kepler's foundation, aiming to find planets close enough for future telescopes to study in detail. The James Webb Space Telescope and future missions will analyze their atmospheres, searching for signs of habitability or even life. But the scale of those searches, the confidence behind them, all trace back to Kepler. It provided the evidence that such searches are worthwhile, because the galaxy is not empty but filled with targets. The story of Kepler is not a story of an instrument alone, but of what it revealed about our relationship to the universe. It showed that the cosmos is not a scattered wilderness, but a connected system of systems, a network of light and gravity producing worlds everywhere. The telescope's fixed gaze turned abstraction into pattern, pattern into certainty. By doing nothing more than watching carefully, it uncovered a structure that had always been there, hidden in plain sight. When Kepler ran out of fuel and its mission officially ended, the spacecraft was left drifting quietly in orbit around the Sun, its instruments powered down but its contribution complete. It had transformed a question into a map. Before it, we had wondered if planets existed elsewhere. After it, we knew they did, in numbers beyond measure. The sky we look up to now is different because of it. Every star that glimmers carries the unspoken implication of unseen companions. The awakening that Kepler brought about is ongoing. Each new mission, each refinement of technique, builds upon its legacy. The methods of finding the invisible, perfected through its observations, continue to expand the census of worlds. The quiet precision of its measurements, the patience of its stare, turned a portion of the sky into a mirror of the galaxy's abundance. Its discoveries, once isolated lines on graphs, now form the foundation of a new cosmic understanding that worlds are the rule, not the exception. Somewhere, within the field of stars that Kepler once watched, planets continue their orbits, crossing the faces of their suns just as they did when the telescope was alive. The light they block still travels through space, unnoticed now, but still there, still carrying the faint rhythm of their motion. The data Kepler recorded captured only a few years of their endless cycles, a small window into their vast history. The universe, indifferent to our observation, continues to move. The telescope, built by human hands and minds, caught a glimpse of that motion and translated it into knowledge. The Kepler awakening was not a moment of noise or spectacle. It was a quiet realization built from years of watching, recording and confirming. It replaced the silence of assumption with the steady hum of evidence. The telescope's unblinking eye gave humanity a new image of the galaxy, not one of stars alone, but of a living expanse filled with worlds. Its mission ended, but its work continues in every observation that follows, in every telescope that turns its gaze to the sky, searching for the small dimming of the light that means another planet is there, circling quietly, unseen but no longer unknown. After the flood of discoveries from Kepler, the quiet rhythm of astronomy changed. The universe, once measured in single points of light and lonely distances, became a field of statistics. The The search for other worlds was no longer a matter of whether they existed, but of how many there were, what types they came in, and what those numbers could tell us about the structure of the galaxy. Data replaced speculation. Instead of dreaming of distant worlds, astronomers began counting them. The sky turned into a set of probabilities, each star a sample in a growing equation that described the galaxy's population of planets. The shift was profound, not because it made the universe smaller, but because it gave its vastness measurable meaning. By the time Kepler ended its mission in 2018, astronomers had confirmed more than 4,000 exoplanets and catalogued thousands more candidates. At first glance, that number seems large, but it represents only a thin slice of what exists. Kepler observed a single region of the Milky Way, a patch of sky smaller than your fist held at arm's length. Yet even in that narrow window, it found an astonishing variety of worlds. By comparing the fraction of stars that showed planets in that field to the total number of stars in the galaxy, scientists could begin to extrapolate. The result was staggering. There are likely between 100 and 400 billion planets in the Milky Way. Some estimates push that number even higher, into the trillions. The numbers alone, vast as they are, tell only part of the story. They reveal patterns hidden within the population. For example, small planets, those roughly the size of Earth or slightly larger, turn out to be far more common than large ones. Super-Earths, worlds with masses between 1 and 10 times that of our own, are among the most frequent types of planets detected. In our solar system, there is no example of such a world. We have small rocky planets like Earth and Mars, and large gas giants like Jupiter and Saturn, but nothing in between. Yet elsewhere in the galaxy, these intermediate worlds dominate. Their prevalence suggests that our solar system, long assumed to be typical, may actually be unusual. Kepler's data also showed that planetary systems are extraordinarily diverse in their architectures. Some stars host tightly packed groups of planets, orbiting close together, completing revolutions in a matter of days. Others have planets spaced widely apart, tracing long, cold paths around their stars. Some systems contain planets orbiting in resonance, where their gravitational interactions lock them into rhythmic relationships. Others appear chaotic, shaped by migrations and collisions long past. The variety is immense, but within it lies order, statistical regularities that reflect the physics of how planets form and evolve. The first step in interpreting these numbers is understanding the limitations of observation. Kepler's field of view contained about 150,000 stars, but only a small fraction of planetary systems align so that their planets transit from our perspective. The rest remain hidden. For every planet detected, there are many more that go unseen. By accounting for this geometry, astronomers can correct the numbers, estimating the true frequency of planets across the galaxy. The math is meticulous but rewarding. The conclusion is consistent. Nearly every star hosts at least one planet. The galaxy is not a scattering of isolated suns, but a continuous fabric of systems. The data from other methods such as radial velocity and microlensing confirm this conclusion. Together they form a coherent picture of planetary abundance. The radial velocity surveys, which detect the wobble of stars caused by orbiting planets, reveal many large planets that the transit method might miss. Microlensing events, rare but powerful, detect planets farther from their stars where transits are unlikely. Each technique fills a different part of the map. When combined, they reveal that planets populate every region of space where conditions allow them to form. There are worlds orbiting close enough to their stars to skim their surfaces, and others so distant that their years last longer than the history of human civilization. The next step is categorization. Astronomers group planets by size, composition, and orbit, building a taxonomy of worlds. Gas giants, like Jupiter and Saturn, are common but not dominant. Neptune-like planets, smaller and denser, appear more frequently. Then there are the super-Earths, planets with thick atmospheres or shallow oceans. their surfaces perhaps shrouded in clouds or ice. At the smaller end are rocky planets roughly comparable to Earth. Their abundance is a quiet revelation. Statistically, there are billions of such worlds orbiting within habitable zones across the Milky Way. Not all are truly habitable, but their sheer number ensures that some must be suitable for life as we know it. Each category has its own story. Hot Jupiters, the first type of exoplanet discovered, orbit perilously close to their stars, their atmospheres heated to thousands of degrees. They were once thought to be rare anomalies, but now we know they form through migration. Giant planets born in colder regions that spiral inward over time. Super-Earths, on the other hand, are stable and common, often forming in systems where multiple such worlds circle in compact flat plains. Their existence challenges models of planet formation based solely on our solar system. Nature, it seems, prefers variety. The numbers also reveal patterns tied to the types of stars. Planets form more readily around certain stars than others. Massive stars, bright and short-lived, tend to have fewer planets, their powerful radiation dispersing the disks of gas and dust too quickly for stable worlds to form. Smaller stars, especially red dwarfs, are prolific planet builders. Their long lifespans and dense disks make them ideal cradles for planetary formation. Because red dwarfs make up the majority of stars in the galaxy, most of the Milky Way's planets likely orbit these faint, cool suns. Many of them reside close to their stars where conditions could allow for warmth and even liquid water. From these findings comes another number, one that carries emotional weight as well as scientific meaning. It is known as Eta Earth, the fraction of stars that host Earth-sized planets in their habitable zones. Estimates vary, but current data suggest that this fraction lies somewhere between 20 and 50%. That means that in our galaxy alone, there could be tens of billions of potentially habitable worlds. Even if only a small fraction of those worlds actually support life, the possibilities are immense. The numbers transform speculation into expectation. Life elsewhere becomes not just possible, but probable. The statistical view of the galaxy extends beyond simple counting. It allows astronomers to reconstruct the history of planetary formation across time. Younger stars, surrounded by remnants of their birth disks, show evidence of planets still forming. Older stars often host stable, mature systems. By studying planets at different stages of development, scientists can trace how systems evolve, how orbits shift, atmospheres escape, and surfaces change. The numbers become a timeline, a demographic portrait of the galaxy's ongoing creation. The precision of these statistics depends on data and patience. Each discovery adds a single data point to an ever-growing sample. Over years and decades, patterns emerge. The rate of discovery itself becomes part of the analysis. As instruments improve, the range of detectable planets expands, revealing types once hidden by noise or distance. With each refinement, the numbers shift slightly, but the general picture remains clear. Planets are everywhere, diverse in form and countless in number. One of the most striking lessons from this numerical exploration is the realization that the Milky Way is not a static structure. It is dynamic, with stars and planets forming, evolving, and sometimes being destroyed. Gravitational interactions between stars occasionally eject planets from their systems, sending them drifting through interstellar space. These rogue planets, unbound to any star, may number in the billions. Some estimates suggest that free-floating worlds could be as common as those bound to suns. The galaxy is not only full of systems, but also of wanderers, planets that travel alone through the dark. Every new estimate carries with it an element of humility. The scale of what exists exceeds comprehension. The numbers we calculate are based on samples of light and motion from small portions of the sky, extrapolated across the entire galaxy. Even so, the consistency of the data across methods, instruments, and regions confirms that the conclusion is sound. Planets are the natural outcome of star formation. The universe builds them wherever it builds stars. The numbers game, as it's often called, is not about reducing the cosmos to figures on a chart. It's about translating the unseeable into something graspable. Each statistic is a bridge between the invisible and the imaginable. When astronomers say that there may be 1 trillion planets in the Milky Way, they are not speaking poetically. They are stating a measurable truth, derived from observation, repetition, and pattern. Behind every number lies light measured, recorded, and interpreted. The implications extend beyond astronomy. The realization that planets are ubiquitous reshapes how humanity understands its own significance. For most of history, Earth was thought to be a singular creation. Even after Copernicus moved it from the centre, it remained in imagination an exception, a rare oasis in an empty expanse. The numbers have erased that isolation. Earth is not alone, not in kind, not in process, not in origin. It is one among billions, part of a continuum of worlds produced by the same cosmic mechanisms. Yet this understanding does not diminish the uniqueness of Earth. If anything, it deepens it. Knowing that there are so many planets underscores the improbable combination of factors that make ours habitable. Among billions of worlds, each with its own balance of light, heat, and chemistry, this one happens to sustain life. The numbers give perspective, not hierarchy. They reveal that the universe is not built around rarity, but around repetition. Life, if it exists elsewhere, will be another expression of that repetition, another outcome of the same laws. As the data continue to accumulate, astronomers refine their models, calculating not just how many planets exist, but how they are distributed by type and orbit. They measure occurrence rates for each category: gas giants beyond the frost line, super-Earths close to their stars, Earth-sized planets in temperate zones. Each fraction refines the larger equation of galactic structure. The Milky Way becomes a statistical landscape, a place defined not by empty distances, but by density, probability, and pattern. Future missions will push these estimates further. Instruments now in development aim to detect planets smaller than Earth, to study their atmospheres in detail, and to search for chemical imbalances that might hint at biological activity. With each improvement, the numbers will become more precise, the uncertainties smaller, but the essential truth will remain the same. The galaxy is full. Its population of worlds exceeds imagination. The emptiness between stars is not void, but space filled with orbits, motions, and possibilities. The numbers game is still in progress. Every year the count grows. Each new detection adds to the pattern that Kepler began, transforming the abstract night into a measurable expanse. The act of counting does not end with a final total. It continues indefinitely, a reflection of the endless process of formation and discovery. In that continuity lies the quiet wonder of astronomy, the understanding that the universe is not something to be completed or summed, but something to be continually revealed. The galaxy remains, as it always has been, a vast system of systems. Stars burn, dust gathers, gravity binds, and planets form. Each new world adds a decimal point to a total that will never stop increasing. The numbers are not a conclusion, but a language, one that translates the silence of the cosmos into something human minds can hold, if only for a moment. The counting will go on as long as the instruments endure, as long as curiosity lasts, and as long as there is light to measure. The more the galaxy revealed itself through data, the clearer it became that there is no single kind of planet, no standard pattern that defines them all. The early discoveries, when seen together, formed not a uniform picture but a gallery of differences. Each world was a separate experiment in gravity, chemistry, and time. The universe, it seemed, was endlessly inventive. In every direction, planets were being shaped into forms that challenged the limits of imagination. The first exoplanets found were giants, massive spheres of gas orbiting close to their stars glowing faintly with heat. They were the easiest to detect because their gravitational pull and their shadows on starlight were large enough to register clearly. These worlds were so close to their suns that their atmospheres must have been stripped and reshaped by radiation. Their winds moved faster than sound, their skies roiled with metallic clouds, and their temperatures rose beyond the melting points of most elements. Yet despite these extremes, they were stable, following predictable orbits. The discovery of such worlds revealed that nature allows for systems far more compact and dynamic than our own. The hot Jupiters, as they came to be called, were only the beginning. As instruments became more sensitive, smaller and cooler worlds began to appear. Super-Earths emerged as one of the most common planetary types, planets between the size of Earth and Neptune. Their masses could range from a few to 10 times that of our planet, with densities that varied widely. Some were rocky, others cloaked in thick atmospheres. Some might have shallow oceans spread across their surfaces, others could be shrouded in clouds of methane or ammonia. The diversity of super-Earths showed that the universe rarely repeats itself exactly. The same physical rules, applied across billions of cases, produce endless variation. Smaller planets closer to the size of Earth also proved common. Many of them orbit stars smaller and cooler than our Sun. Red dwarfs, the most numerous type of star in the galaxy, often host planets packed tightly in close orbits. Because these stars burn slowly and live for trillions of years, their planets have time for climates to stabilize, for atmospheres to evolve, for chemistry to change. Some of these worlds may be tidally locked, with one side in perpetual day and the other in endless night, their skies divided between blazing heat and frozen darkness. Others might rotate slowly enough to distribute warmth evenly, allowing thin bands of habitability around their terminators where day meets night. Farther from their stars, where temperatures drop and sunlight weakens, planets take on other forms. Gas giants and ice giants dominate those regions, their thick atmospheres holding layers of clouds under immense pressure. Beyond them may lie worlds composed largely of water and ice, mixtures of frozen gases and exotic ices that form only under extreme conditions. The outer regions of planetary systems are colder, but no less complex. Their moons, often as large as small planets, can harbour subsurface oceans and geologic activity. In our own system, places like Europa, Ganymede and Enceladus remind us that even in the cold, life-supporting chemistry can persist beneath protective layers of ice. If such conditions exist here, they likely exist elsewhere too, multiplied across billions of systems. Among the most unusual worlds discovered are those known as lava planets. These are rocky bodies orbiting so close to their stars that their surfaces are oceans of molten rock. Their atmospheres are filled with vaporized minerals, and their day sides glow with thermal radiation. On some, the temperature difference between the star-facing and shadowed sides is so extreme that material evaporates on one side and condenses on the other, creating a cycle of stone rain and vaporized rock storms. These planets exist at the very edge of stability, where the proximity to their stars nearly tears them apart, yet gravity holds them together in balance. Others lie at the opposite extreme, planets so distant from their suns that they receive almost no warmth. These frozen giants drift through the outer reaches of their systems, where light from their stars is little more than a glimmer. Their atmospheres may contain clouds of ammonia and methane, and their surfaces could be crusted with frozen gases. Some may have internal heat sources, generated by slow radioactive decay or residual energy from their formation, creating layers of liquid deep beneath the ice. In those hidden depths, conditions could exist that remain stable for eons. Between these extremes lie worlds of every conceivable type. Some orbit binary stars moving in figure-8 patterns around two suns. In such systems, the light and shadow change in ways unknown on Earth. The temperature shifts with each orbit as one star rises while the other sets, creating rhythms of heat and cold that could shape strange and dynamic climates. Other planets orbit triple or even quadruple star systems, locked in complex gravitational dances that remain stable only through delicate balance. These configurations, once thought improbable, turn out to be natural outcomes of the galaxy's mechanics. There are also rogue planets, worlds that wander alone through space, unbound to any star. They may have been ejected from their systems by gravitational encounters or formed directly from collapsing clouds of gas without ever igniting as stars. These lonely planets drift in darkness, warmed only by their internal heat. Some may have thick atmospheres that trap enough warmth to keep subsurface oceans liquid, even in the absence of starlight. In the silent interstellar void, such planets travel endlessly, unseen except when they briefly pass in front of background stars, bending their light for a moment before disappearing again. The range of conditions among planets extends beyond what we can easily categorize. Some worlds may have atmospheres dominated by hydrogen, others by nitrogen, carbon dioxide, or exotic compounds unknown to Earth. Their skies could be red, orange, or violet, depending on the chemistry of their air and the colour of their suns. Clouds could be made of water, methane, sulfuric acid, or silicate dust. Winds could move faster than hurricanes, or there might be no wind at all, only stillness under heavy air. The variety of climates, pressures, and compositions is vast. Each planet represents a distinct combination of initial conditions, shaped by chance and governed by physics. Understanding this diversity requires more than counting. It demands models of how planets form and evolve. Observations suggest that most planets begin in protoplanetary disks, rings of dust and gas orbiting newborn stars. Within those disks, particles collide and stick, forming clumps that grow into planetesimals and eventually into full planets. The outcome depends on countless factors: the mass of the disk, the temperature gradient, the chemical composition, the timing of collisions. Even small differences can lead to drastically different worlds. The process is chaotic, yet the result is structured. The galaxy's billions of planets are the natural consequence of matter following simple rules under gravity. Among these worlds, certain patterns emerge. Smaller rocky planets tend to form closer to their stars, where heavy elements condense. Larger gaseous planets form farther out, where ice and gas are more abundant. But migration, planets moving inward or outward after formation, complicates this order. Many systems show evidence of planets that have shifted dramatically from their original positions, perhaps driven by gravitational interactions with other planets or with the disk itself. These migrations create systems that look very different from ours, with giants orbiting close in and smaller worlds scattered farther out. The diversity of arrangements is as telling as the diversity of planets themselves. The study of exoplanet atmospheres has added another layer to this picture. When a planet transits its star, some of the starlight passes through its atmosphere, leaving traces of absorption that can be measured. By analysing those traces, astronomers can identify molecules present in the air. Water vapour, methane, carbon monoxide, sodium and potassium have all been detected on distant worlds. These findings reveal not only composition but also temperature, weather, and even wind speed. The atmospheres of exoplanets are laboratories of chemistry, operating on scales and under conditions we cannot replicate on Earth. The discovery of planets of every kind has also reshaped the way scientists think about habitability. The traditional definition, a planet in the right temperature range for liquid water, has expanded. Moons with subsurface oceans, planets with thick atmospheres that trap heat, or even rogue planets with geothermal activity could all provide environments where life might arise. The possibilities are no longer confined to narrow ranges. Life, if it exists elsewhere, might thrive in forms adapted to conditions far beyond our own. Each new detection adds to the mosaic. The galaxy's inventory grows richer with every observation, and patterns begin to connect across systems. There are planets that resemble scaled versions of Earth, others that mirror the icy giants of our outer solar system, and countless others that defy comparison. The naming conventions, super-Earth, mini-Neptune, hot Jupiter, are human attempts to impose order on a spectrum of variation. In truth, every planet is its own category, its own experiment in cosmic design. The diversity also hints at the underlying unity of physics. Despite the differences, all planets obey the same laws of motion, the same principles of thermodynamics, the same processes of formation. Their variety is not random but structured by probability and environment. The universe builds complexity from simplicity, repetition from variation. Every world, no matter how strange, is part of that continuum. The more we learn about these planets, the more we see echoes of ourselves among them, not in the details of their surfaces or skies, but in their existence. They are the inevitable result of the same forces that made our own world. Gravity gathered matter, heat shaped it, time solidified it. Each planet in its orbit is a testament to the universality of those processes. Whether molten, frozen, gaseous, or rocky, each follows the same quiet rules. As instruments become more powerful, the catalogue of known planets grows faster than ever. Space telescopes now identify thousands each year. Some are near enough for follow-up studies, their atmospheres measurable, their masses confirmed through multiple techniques. Others lie so far away that only their shadows betray them. The data accumulate, and with it comes a clearer sense of scale. The Milky Way's diversity of planets is not a set of exceptions, but the defining feature of the galaxy itself. In that diversity lies a kind of balance. The extremes, lava worlds, ice giants, ocean planets, and gas behemoths form the edges of a spectrum. Between them are countless gradations, each shaped by unique histories. The galaxy's creativity is statistical, not deliberate. It is the outcome of chance operating on vast numbers. Given enough stars, enough disks, and enough time, every possible configuration will eventually exist somewhere. Even as we catalogue these worlds, our understanding remains incomplete. There are planets so faint, so distant, or so cold that we may never detect them. Others may exist in forms we have not yet imagined. Worlds without solid surfaces, planets shrouded in perpetual storm, or bodies composed of materials rare on Earth. The diversity we see is only a fraction of what exists. But even this fraction reveals that the galaxy is not uniform or predictable. It is an ongoing experiment in variety. The phrase, planets of every kind, is not exaggeration. It is literal description. The universe produces planets wherever conditions allow, and it allows for nearly everything. From the furnace-like orbits near bright stars to the frozen edges of darkness, where starlight never reaches, worlds exist. Some are bound, others free. Some are stable for billions of years. Others last only briefly before being torn apart. Each contributes to the ongoing story of formation and transformation that defines the galaxy. The planets we have found are the first representatives of an almost infinite range. Their existence confirms that the universe is far more dynamic and fertile than anyone once imagined. Every type of planet we can conceive, and many we have yet to conceive, likely exist somewhere. The process that forms them is simple, but the outcomes are endlessly complex. Matter falls together, gravity holds it, and time refines it. Out of that simplicity, entire worlds emerge. Even now, as new telescopes prepare to search farther and deeper, the variety continues to grow. The boundaries between categories blur, and the differences that once seemed defining become gradients. The idea of a typical planet fades. The only constant is diversity itself. In that realization lies the quiet truth of the galaxy. There are planets of every kind because the universe makes them in every possible way. As astronomers learned to count the planets and classify their kinds, one question began to take shape beneath the data. It was not about number or orbit or mass. It was about balance. Among the billions of worlds spread across the galaxy, some must exist under conditions neither too hot nor too cold, neither too close to their stars nor too far away. The quiet, statistical truth implied something intimate, that the physics of light and distance might conspire to create a narrow zone where liquid water can exist, where chemistry can unfold, where life, in some form, might begin. The search for that balance came to be known as the search for the habitable zone, and its most familiar metaphor was drawn from an old story, the Goldilocks zone. Not too this, not too that, just right. The idea was simple in outline but rich in consequence. Every star emits light and heat. Planets orbiting close to that star receive more energy. Those farther away receive less. If a planet is too close, its water, if it has any, evaporates into vapor and escapes. If it is too far, water freezes solid and remains locked beneath ice. Somewhere between those extremes lies a distance where the energy received is enough to keep water liquid on a planet's surface. That liquid phase matters because water, as chemistry's universal solvent, allows molecules to interact, dissolve, and combine in complex ways. It provides a medium where life, at least as we know it, can emerge and persist. When scientists first began applying this idea to exoplanets, they worked from the only example they knew, Earth. They measured the amount of solar energy our planet receives and calculated how far a planet could be from a similar star and still maintain a temperate surface. The result was a set of simple numbers. For a star like the Sun, the habitable zone stretches roughly from 0.95 to 1.37 astronomical units, with Earth comfortably in the middle. For brighter stars, the zone moves outward. For dimmer stars, inward. It was a framework that could be applied to every system. The Goldilocks zone became a way of mapping potential habitability across the galaxy. But the simplicity of the model was deceptive. A planet's ability to host liquid water depends on more than distance. Atmosphere plays a decisive role. Carbon dioxide, water vapor, and methane trap heat, extending the range of possible habitability. A dense atmosphere can keep a planet warm even when it orbits far from its star, while a thin atmosphere can make even a close world freeze. Clouds reflect sunlight, altering temperatures further. Geological activity, rotation rate, magnetic field, and even the presence of oceans all influence how energy circulates. The Goldilocks zone, though convenient to define, is not a fixed ring around a star. It is a shifting conditional space determined by the balance of many factors. The earliest attempts to apply this idea beyond our solar system began cautiously. As Kepler and other missions found thousands of exoplanets, astronomers calculated which ones might lie within their star's habitable zones. These were called potentially habitable planets, not declarations of life, but locations where liquid water could, in theory, exist. Each discovery added a new point of possibility. Planets like Kepler-22b, orbiting within that gentle band, became symbols of curiosity. The data suggested that billions of such worlds might exist in the Milky Way alone. The idea of a Goldilocks planet appeals because it links the abstract vastness of the galaxy to something familiar. Earth itself is a Goldilocks planet, balanced delicately between freezing and boiling, shielded by an atmosphere that moderates temperature and recycles water. It exists in a region where sunlight provides just enough warmth to sustain oceans and life. The more scientists understand about this balance, the clearer it becomes that it is neither simple nor static. Over time, the sun's brightness has increased, and Earth's atmosphere has changed to compensate. The planet's climate has fluctuated, sometimes drastically, but feedback mechanisms, volcanic outgassing, chemical weathering, biological regulation, have kept conditions within the narrow band that allows life to continue. That self-regulating capacity, known as the Gaia hypothesis in its more poetic framing, may be as important to habitability as the distance from the star. Among the many worlds now known, some appear to sit within their own Goldilocks zones. The star TRAPPIST-1, a small, cool red dwarf about 40 light-years away, hosts at least 7 planets, 3 of which orbit within the region where surface temperatures could permit liquid water. These planets are all roughly Earth-sized, packed close to their faint star. Their days and nights are likely permanent on opposite hemispheres, one side illuminated constantly, the other in darkness. If they have atmospheres thick enough to circulate heat, they might support stable climates, at least in theory. The system has become one of the most studied in astronomy, a natural laboratory for testing ideas about habitability. Other systems offer similar intrigue. Proxima Centauri b, orbiting the nearest star to the Sun, lies in its star's habitable zone, though subject to intense stellar flares that could strip its atmosphere. LHS 1140b, another nearby planet, orbits within a range where water could exist and may possess a dense atmosphere that protects it from radiation. Kepler 452b, sometimes nicknamed Earth's cousin, orbits a star slightly older and larger than the Sun at a distance that places it squarely in the habitable zone. Each of these worlds exists as a point of data and a point of reflection, a reminder that the delicate balance we experience is not unique. But even with these discoveries, the Goldilocks concept remains a starting point rather than an answer. The more we learn about planetary diversity, the clearer it becomes that habitability is not confined to a narrow band of distance. Venus, though similar in size to Earth, lies just a little closer to the Sun, yet that small difference, amplified by atmospheric runaway, turned it into a furnace. Mars, a little farther out, once had flowing rivers and lakes, but its smaller mass allowed its atmosphere to thin and its warmth to fade. Between them lies Earth, balanced by circumstance and feedback. This small comparison within one solar system illustrates how fragile the balance is and how easily it can shift. The search for habitable worlds now extends beyond simple temperature ranges. Astronomers examine atmospheric composition through spectroscopy, looking for signs of gases that might indicate equilibrium out of balance, an indicator of life. On Earth, the coexistence of oxygen and methane in the atmosphere is sustained by biology. Without continuous replenishment, such gases would react and disappear. Detecting similar combinations elsewhere could point to active processes, biological or otherwise. Instruments like the James Webb Space Telescope are beginning to make such measurements, peering into the atmospheres of exoplanets to look for water vapor, carbon dioxide, and other markers. The Goldilocks mystery is not only about distance or chemistry, it is about the interplay of time. Planets and stars evolve. A world that is habitable today may not have been so in the past, and may not remain so in the future. Stars brighten as they age, shifting their habitable zones outward. Planets migrate, tilt, and change atmospheres. The conditions that allow liquid water are transient, appearing and vanishing over geological timescales. The fact that Earth's climate has remained stable enough for life over billions of years is not guaranteed by physics alone, but by a combination of feedbacks, chance, and evolution. The realization that habitability is dynamic rather than static has deepened the mystery. It suggests that many planets may pass through habitable phases, brief windows of possibility before freezing or boiling away. Others may cycle repeatedly between extremes, their climates oscillating over eons. In this view, the galaxy is full of planets that have been habitable, will be habitable, or are habitable now. Life, if it arises easily under the right conditions, may appear and vanish just as frequently, scattered through time as well as space. The study of these possibilities continues to expand. Climate models simulate conditions on distant worlds, testing how temperature, rotation, and atmosphere interact. Laboratory experiments explore how different mixtures of gases and minerals respond to heat and pressure, hinting at the range of possible chemistries. Observations refine estimates of stellar activity and magnetic protection, helping to determine which planets might retain their atmospheres. Each factor adds a layer to the understanding of what makes a planet just right. The Goldilocks mystery also extends to moons. In our solar system, moons like Europa and Enceladus, though far from the Sun, contain oceans beneath their icy crusts. These oceans remain liquid due to heat generated by tidal flexing, gravitational energy converted into warmth as the moons are stretched and compressed by their parent planets. If similar mechanisms operate elsewhere, then habitable environments could exist even outside traditional habitable zones. The search for life thus expands to include not only planets, but their satellites, increasing the number of possible abodes by orders of magnitude. Every discovery feeds into the same quiet realization. The universe favors balance through variety. The conditions that sustain liquid water and complex chemistry are rare in isolation, but abundant in repetition. Among billions of systems, the odds that some achieve the right combination of factors are overwhelming. The mystery lies not in whether such worlds exist, they clearly do, but in how they sustain that balance and what may arise from it. Even as the data accumulate, the concept of the Goldilocks zone remains an approximation, a human simplification of a process far more intricate. Planets are not static objects. They breathe, shift, and evolve. Their climates are shaped by volcanism, plate tectonics, and the interactions of their atmospheres with stellar winds. Their fates are tied to the life cycles of their stars. The balance we seek to define is not a fixed state, but a dynamic equilibrium, a dance between energy and matter maintained only for as long as the forces remain in proportion. The search for worlds that share this balance continues with every telescope pointed skyward. Each detection of a planet in a habitable zone is an invitation to study further, to measure its atmosphere, to refine its temperature, to model its surface. With each step, the mystery grows richer, not because it resists explanation, but because it expands in complexity. The more we learn, the more variables appear, and the more we understand that habitability is not a simple question, but an entire spectrum of possibilities. The Goldilocks mystery endures because it connects the vastness of the galaxy to something familiar, the experience of a world that feels, to us, perfectly placed. It is a mystery not of rarity, but of relationship. The relationship between light and matter, between star and planet, between stability and change. The universe, in its endless variation, produces balance not as an exception, but as part of its pattern. Somewhere, among the billions of worlds we have yet to see, others must exist within their own zones of comfort, their own narrow bands of possibility. As observation improves, we will identify more of these balanced worlds, each offering a glimpse into the range of nature's equilibrium. Some will resemble Earth, others will differ completely. But all will share the same fundamental truth. They are outcomes of the same cosmic process, results of gravity, light, and time working together. The Goldilocks mystery is not about searching for replicas of our planet, but about understanding how the universe constructs and sustains balance amid chaos. It is the recognition that life's potential is woven into the very mechanisms that shape the stars and the spaces between them. Among the discoveries that followed the great wave of exoplanet research, few were as unsettling and beautiful as the realization that not all planets belong to stars. For centuries, the concept of a planet was inseparable from the image of a central sun. The idea of a world implied orbit, light, and warmth. Yet as astronomers examined the galaxy with more sensitive instruments, they began to find evidence for something stranger. Planets adrift in darkness, travelling alone through interstellar space. These worlds, unbound to any star, are known as rogue planets. They do not reflect the light of a nearby sun. They are invisible to ordinary telescopes, detectable only through rare alignments or faint glimmers of their own residual heat. Their existence expands the very definition of what a planet can be. The first hints of such objects emerge from theoretical models rather than observation. As simulations of planetary formation improved, astronomers realized that gravitational interactions in young systems could be violent. When planets form, they do not settle immediately into stable orbits. They pull on one another, exchanging momentum, sometimes colliding, sometimes ejecting each other entirely. A single close encounter between a giant planet and a smaller companion can fling the smaller one outward with enough speed to escape the system's gravity. Once free, it drifts away, carrying its atmosphere and history into the cold. Over millions of years, countless such ejections would occur, populating the galaxy with unanchored worlds. The models predicted that for every starbound planet there might be one or more set loose. For a long time, these predictions remained abstract. A planet without a sun would be almost impossible to detect directly. It would emit no reflected light and would quickly cool after its formation. But physics provides indirect paths to discovery. Gravitational microlensing, a technique that measures the way a massive object bends and amplifies the light of a background star as it passes in front of it, offered a way to find them. When a rogue planet crosses the line of sight between a distant star and Earth, the light from that star briefly brightens and then fades. The event lasts only days or hours, but the pattern of that brightening reveals the mass of the lensing object. In the early 2000s, astronomers began detecting microlensing events that could not be explained by stars or binary systems. The lenses were too small, their durations too brief. The data suggested that they were caused by objects with masses similar to planets, worlds drifting freely through the galaxy. Subsequent surveys, including projects like OGLE and EMOA, gathered more such events, confirming that these rogue planets were not rare anomalies, but part of the galactic population. Their numbers, though uncertain, appeared vast. Some estimates suggested that free-floating planets might be as common as those bound to stars. The Milky Way, once imagined as a collection of suns, revealed itself as an ocean where worlds move both in orbit and in solitude. The idea of a planet without a sun feels paradoxical, yet it follows naturally from the same laws that govern the rest of cosmic evolution. The processes that build planets are messy. Collisions, migrations, and ejections are part of how systems find stability. In the early years of a star's life, its surrounding disk of dust and gas teems with motion. Clumps of material form, merge, and sometimes scatter. Gravitational encounters reshape orbits until balance is achieved. The ones that are thrown free become wanderers. They leave behind their stars but retain the internal heat generated by their formation. For a time, millions or even billions of years, they may glow faintly in the infrared, slowly radiating their warmth into space. As they cool, their surfaces change. A rogue planet the size of Jupiter might retain enough internal heat to remain gaseous and dynamic, its deep atmosphere swirling in darkness. A smaller rocky planet would cool more quickly, its surface freezing solid. Yet even such a frozen world might not be entirely lifeless. Beneath layers of ice, residual heat from radioactive decay could keep interior oceans liquid. If those oceans contain chemical gradients, as Earth's do, they might support simple chemical activity, perhaps even primitive forms of metabolism. Life on such a world would not rely on sunlight, but on energy from within. The concept of subsurface habitability has grown in importance as scientists study icy moons within our own solar system. Europa, Enceladus, and Titan all harbour internal oceans beneath their frozen exteriors. Their energy comes not from sunlight, but from tidal flexing, the gravitational stretching caused by their orbits around larger bodies. On a rogue planet, that same internal energy could come from residual heat and radioactive decay. If thick layers of ice insulate the interior, the heat could persist for billions of years. Under those conditions, liquid water and stable chemistry could exist in perpetual darkness. Such possibilities have led to the notion that rogue planets might serve as isolated incubators of life. The absence of sunlight would limit complexity, but the chemistry of life requires only energy and stability, both of which could exist underground. The universe may therefore contain not only sunlit worlds with oceans and skies, but also countless dark planets, where heat and water coexist in silence. The diversity of possible environments grows again, extending habitability into places once dismissed as barren. Detecting these worlds directly remains a technical challenge. The faint heat they emit is best observed in the infrared, but even then, the signal is weak. Large surveys with sensitive detectors, like those conducted by space-based telescopes, continue to search for them. Occasionally, a massive rogue planet is detected through its glow, warm enough, young enough, and close enough to reveal itself as a faint point of light against the background. These detections confirm what models long predicted, that free-floating worlds exist in great numbers, from gas giants to smaller rocky bodies. Some may not have been ejected at all. In dense regions of space where clouds of gas collapse to form stars, conditions sometimes allow smaller fragments to condense independently. These objects form directly, like stars, but without sufficient mass to ignite nuclear fusion. The result is a spectrum of bodies between planets and brown dwarfs, often called sub-brown dwarfs or planetary mass objects. They are born in isolation, never attached to any system. The line between star and planet blurs, replaced by a continuum of formation mechanisms. In this way, the galaxy becomes not a structured arrangement of systems, but a continuum of objects, from blazing stars to cold, dark wanderers. The light we see in the night sky represents only part of its content. Between the stars in the spaces we call empty, countless unseen worlds drift silently. Their presence adds texture to the galaxy's structure, mass to its spiral arms, and possibility to its history. They are reminders that the boundaries we draw between categories star, planet, moon are conveniences for understanding, not divisions inherent in nature. The dynamics that create rogue planets also reveal the restless nature of planetary systems. Even stable systems like our own bear traces of past migrations. Jupiter and Saturn, in their early histories, may have moved inward and outward, reshaping the orbits of smaller bodies. The asteroid belt may be the remnant of material prevented from forming a planet by their influence. In other systems, similar interactions can lead to more violent outcomes. When two giant planets approach too closely, their gravitational encounter can fling one outward. The ejected world carries with it the momentum of the system's early chaos, leaving behind a rebalanced set of survivors. Over the lifetime of the galaxy, such events occur uncounted times, ensuring that interstellar space is never truly empty. In regions of the galaxy where stars are densely packed, such as stellar clusters, the process is even more common. Young stars form close together, their gravitational fields overlapping. As planets form and migrate, they are vulnerable to perturbations from neighbouring stars. A close encounter can strip a planet from its host entirely. In this way, clusters become factories of rogue planets, releasing them into the wider galaxy. Once free, they follow paths determined by the overall gravitational field of the Milky Way, drifting through its spiral arms on trajectories that may take them thousands of light years from their birthplaces. The physical reality of these wanderers challenges the traditional image of a planet as a sunlit sphere in orbit. They are dark worlds, illuminated only by the faint glow of the galaxy around them. If one could stand on the surface of a rocky rogue planet, the sky would be filled not with a nearby sun, but with the dim light of countless distant stars. The horizon would never brighten. The temperature would remain fixed by the slow leakage of internal heat, and the passage of time would be marked not by days and nights, but by the slow drift of constellations. The concept of a year would have no meaning. Motion would be endless and directionless, a journey through the interstellar void without destination. In imagining these places, one begins to grasp the scale of the galaxy, not just in distance but in diversity. The presence of worlds without suns expands the definition of what a planetary environment can be. It suggests that planetary formation is not a rare accident but a fundamental feature of cosmic evolution. Wherever matter gathers under gravity, worlds arise. Some remain tethered to the light that gave them birth. Others are cast into darkness. Both outcomes are natural. The galaxy's architecture includes not only systems of stars and planets, but also an uncounted population of solitary worlds moving between them. The study of these rogue planets is still in its early stages. Future surveys, using both microlensing and infrared imaging, will refine estimates of their abundance. Instruments capable of detecting faint heat signatures across wide fields of view may one day map their distribution. Each detection will add to the growing picture of the galaxy's hidden mass. If rogue planets are as numerous as some models suggest, they could contribute significantly to the galaxy's gravitational makeup, influencing its dynamics on large scales. The implications extend beyond statistics. The existence of so many free-floating worlds blurs the distinction between planetary and interstellar environments. It suggests that the raw material of planetary formation is not confined to the vicinity of stars, but is distributed throughout the galaxy. Each rogue planet carries with it the chemical imprint of its origin: water, carbon, silicates, metals, dispersed through space over billions of years. In this way, they act as agents of mixing, spreading elements between systems. Some may eventually be captured by new stars, joining fresh planetary families and continuing their journeys under new suns. The concept of capture is more than theoretical. When a star passes near a rogue planet, gravitational interaction can slow the planet enough for it to fall into orbit. Such events are rare but inevitable over cosmic timescales. A star born into the company of a wandering world gains a new companion. The captured planet carries its history into a new system, its composition and structure different from the native planets. In this way, systems can gain diversity, not only through internal formation, but through adoption. The galaxy's complexity grows through exchange as well as creation. Worlds without suns remind us that planetary formation is not confined to the orderly, illuminated spaces we can easily observe. It extends into the dark, the cold, and the silent. The galaxy is filled with light, but it is equally filled with shadows. The two coexist, forming a whole that cannot be understood by studying only the bright parts. Rogue planets occupy that unseen half of the picture, the portion of existence that continues quietly beyond the reach of starlight. They are not anomalies, but expressions of the same natural processes that govern everything else. Their solitude does not mark them as failures of formation, but as outcomes of motion and time. Each one drifting between the stars carries the same fundamental elements found everywhere: hydrogen, oxygen, carbon, iron, bound together in new configurations. They are the silent travellers of the galaxy, reminders that even in the absence of light, the universe continues to build and move. As the count of planets grew into the thousands, and then into the tens of thousands, astronomy began to look outward again, away from the individual worlds and toward the structure that held them all. The discoveries of exoplanets and rogue wanderers had shown that the Milky Way was not a field of solitary stars, but a vast continuous system of systems. Every point of light was a home, a centre, a gravitational well where planets turned and moons followed. Yet to understand what that meant on a larger scale, it was necessary to consider how all those systems fit into the larger architecture of the galaxy itself. The Milky Way is immense beyond direct comprehension. From the centre to the outer edge, it spans roughly 100,000 light-years, a flattened spiral of stars, gas, dust and dark matter. Within that structure are about 400 billion stars, perhaps more. Each one moves through the galactic disk, following paths shaped by the combined gravity of everything else. To the eye, the galaxy appears serene, a slow swirl of light seen edge-on in photographs. In truth, it is a place of constant motion, where stars orbit the centre like droplets in a vast whirlpool. The Sun itself, with its retinue of planets, is one of those droplets, moving through space at hundreds of kilometers per second, taking about 230 million years to complete a single revolution around the galactic core. Within this structure, order and chaos coexist. The galaxy's spiral arms are not fixed objects but patterns of density, regions where matter temporarily crowds together before dispersing again. Stars form within those arms, lighting up clouds of gas and dust. Over time, the newborn stars drift away, leaving the pattern intact even as its members change. It is a wave, not a wall, a ripple of gravity moving through space. The planets that form around these stars inherit that same motion. They are born in clusters and then scattered, their systems migrating together through the disk. Each solar system is a microcosm of the larger structure, bound to its star but carried along by the galaxy's rotation. The architecture of the Milky Way is layered. At its heart lies a dense bulge of old stars surrounding a supermassive black hole 4 million times the mass of the Sun. This region is compact and energetic, a place where stars crowd together and gravitational forces are intense. Around the bulge stretches the thin disk, where most of the galaxy's stars and planets reside. It is within this disk that the spiral arms trace their luminous curves, forming the backdrop of the night sky we know. Above and below the disk lies a thicker halo of older stars and dark matter, extending far beyond the visible edge. Scattered within that halo are globular clusters, ancient spherical collections of stars that orbit the galaxy like satellites. Each layer has its own composition, age, and history. Planets exist in all of these regions, though in different ways. The inner regions, rich in metals and heavy elements, are fertile grounds for planet formation. The outer halo, made mostly of older, metal-poor stars, hosts fewer planets, since the materials needed to build them were scarce in the early universe. Over billions of years, as generations of stars lived and died, the galaxy enriched itself with heavier elements forged in stellar cores. Those elements, carbon, oxygen, silicon, iron, became the building blocks of new planets. The architecture of the galaxy is not static. It is a cycle of creation and dispersal, with each generation of stars contributing material for the next. The Sun's position in this architecture is modest. It lies in a quiet region between two spiral arms, about 27,000 light-years from the galactic center. This location, sometimes called the galactic habitable zone, offers a balance between density and stability. Closer to the center, radiation and gravitational disturbances are stronger and stellar encounters more frequent. Farther out, the density of heavy elements decreases, making planet formation less efficient. In the middle regions, the environment is steady enough for complex systems to persist, but rich enough in materials to form them in the first place. The Earth, and by extension humanity, exists in a region neither too crowded nor too empty, a galactic Goldilocks zone on a grand scale. Within that region, the stars move in ordered disarray. Each follows its orbit, but the collective result is a slow, churning current. The spiral arms rotate at a different speed than the stars themselves, creating zones of compression where new stars continually form. Giant molecular clouds collapse under their own gravity, giving birth to clusters of suns, each surrounded by disks of gas and dust. Within those disks, planets form, collide, and settle into orbits. Over millions of years, the clusters disperse, spreading their stars and their planetary systems throughout the disk. The architecture of the Milky Way is, in essence, a self-sustaining factory. Stars make planets. Planets enrich the galaxy when they are destroyed, and their material becomes the seed for new generations. The diversity of planetary systems reflects the diversity of the galaxy's environments. In dense star-forming regions where stars are born close together, gravitational interactions can strip or destabilize planetary systems. In quieter regions like the one the Sun inhabits, systems can remain stable for billions of years. The structure of the galaxy therefore influences not only where planets form, but how long they endure. The balance between creation and disruption defines the pattern of habitability on a galactic scale. Over time, stars migrate outward and inward through the disk, exchanging places in a process called radial mixing. This motion blends the populations of stars and planets, smoothing the gradients of composition across the galaxy. The Sun itself may not have been born where it now resides. Evidence from isotopic ratios suggests that it formed in a cluster that has long since dispersed, perhaps several thousand light-years away from its current position. The planets it carries, Earth among them, are passengers in a slow, vast orbit through a changing environment. The galaxy's structure is not fixed architecture, but motion in equilibrium. The relationship between planetary formation and galactic structure extends even further. The density waves that create spiral arms not only trigger star formation, but also determine the timing of when and where new systems arise. As the Sun orbits the centre of the galaxy, it periodically passes through these arms. Each passage exposes the solar system to regions of higher radiation, denser gas, and greater gravitational influence. Some researchers have speculated that these cycles may influence conditions on Earth over geological timescales, perhaps even contributing to patterns of biological evolution and extinction. The idea remains debated, but it illustrates the continuity between planetary and galactic processes. Beyond the disk, the halo holds the relics of earlier epochs. Many of its stars formed before the spiral structure emerged, and their metallicity, astronomy's term for the abundance of elements heavier than helium, is low. Few of them host planets, but some do. The detection of planets around such ancient stars shows that even in the universe's youth, when heavy elements were scarce, planet formation could still occur, albeit in simpler forms. These ancient worlds orbit stars that have survived nearly as long as the galaxy itself. They are fossils of the early cosmos, silent witnesses to more than 10 billion years of history. The galactic architecture is not limited to stars and planets. Between them lies the interstellar medium, a mixture of gas, dust, and cosmic rays that fills the space within the disk. This material serves as both the residue and the source of star formation. It carries molecules, carbon monoxide, ammonia, water, and others, spread across vast clouds light-years wide. Within those clouds, chemistry unfolds in slow motion, assembling the ingredients that will one day form new systems. In this way, the galaxy's structure is not just spatial, but temporal. Every region represents a different stage in a continuous cycle of creation. Dark matter, though invisible, provides the framework that holds all of this together. Its gravity shapes the galaxy's rotation curve, keeping the outer stars moving faster than visible matter alone would allow. The halo of dark matter extends far beyond the luminous disk, forming the unseen skeleton of the Milky Way. Planets, stars, and gas all move within this invisible framework, their orbits bound by its mass. The presence of dark matter reminds us that most of the galaxy's structure lies beyond direct observation. What we see, the stars, the nebula, the clusters, is only the surface of a much deeper architecture. From a planetary perspective, this vast structure may seem abstract, yet it defines the environment in which all worlds exist. The distribution of elements, the density of nearby stars, the frequency of supernova, all are determined by galactic structure. These factors influence the likelihood of planets forming, surviving, and sustaining life. A planet's sky, its chemistry, even its stability over billions of years, are connected to the position of its star within the galactic framework. The architecture of the Milky Way is not distant or separate. It is the background condition of every local story. When viewed from the outside, galaxies like ours are common. Spiral galaxies are among the most efficient engines of star and planet formation in the universe. They balance density and motion, providing regions where material can accumulate without collapsing entirely. Each spiral arm is a moving front of creation, producing stars that, in turn, produce planets. The Milky Way's architecture is a scaled reflection of that larger universal pattern. The same principles that shape a solar system shape a galaxy, only on vastly different scales. The discovery of exoplanets has begun to extend even beyond our galaxy. A few detections made through micro-lensing suggest that planets also exist in other galaxies, orbiting stars tens of millions of light-years away. Though indirect, these observations imply that planetary formation is a universal process, not confined to the Milky Way. If every galaxy builds stars and every star builds planets, then the architecture of worlds extends across the cosmos. The Milky Way, with all its complexity, is one among billions of similar structures, each filled with its own systems of light and shadow. Within this grand framework, the planets of the Milky Way trace their own smaller orbits, each governed by local conditions but participating in the larger motion of the galaxy. Over billions of years, some systems will pass close to others, exchanging material or even losing planets to interstellar space. Others will remain isolated for the entirety of their existence. The pattern of their distribution reflects both the order of formation and the randomness of motion. The galaxy's architecture is not static geometry, but fluid dynamics on a scale so vast that it appears still. The idea of galactic architecture transforms how we think about planets. They are not isolated accidents, but integral components of a larger system. The same processes that maintain the spiral arms that circulate material through the disk also shape the frequency and character of planets. The structure of the Milky Way determines the rhythms of planetary creation, destruction, and renewal. It is a cosmic ecology, with energy and matter cycling through scales of space and time far beyond human experience. And within that immense system, the Sun continues its orbit, carrying Earth and its neighbours with it, threading through regions of denser and thinner material, through arms of star formation and stretches of quiet darkness. The galaxy turns, and everything within it turns with it. Each planet, whether orbiting or drifting, participates in the architecture of motion that defines the Milky Way. The structure is both grand and intimate, both stable and alive. It is the shape of the galaxy's memory, built from light, dust, and time, and within it, every world finds its place. As the count of planets rose into the billions, and the evidence of worlds beyond number accumulated, one thought began to linger beneath the surface of every discovery. It was not about the mechanisms of orbits, or the compositions of atmospheres, but about presence. The instruments had shown that the galaxy was full of planets, rocky, gaseous, frozen, molten, close and far, lit and dark. But among all that abundance, one question remained. How many of those worlds carry life? The more planets astronomers found, the more the scale of the question expanded. It was not a mystery of numbers, but of existence. The search for other minds, other forms of organisation and awareness, became a quiet extension of everything learned so far. The idea that life might exist elsewhere is as old as astronomy itself. In ancient times, thinkers imagined the heavens as populated by gods or spirits. Later, as the concept of infinite worlds emerged during the Renaissance, philosophers speculated that each star might host its own version of Earth. These were intuitions born of wonder, not evidence. For centuries there was no way to test them. Life remained a concept tied to one planet, and the cosmos was studied as a place of matter, not of biology. Only in the last few generations has that boundary begun to shift, as science learned to read not just light, but the signs of chemistry and time hidden within it. The modern search for life began not with exoplanets, but with the exploration of our own solar system. Mars, with its polar caps and surface features, was once thought to harbour vegetation and perhaps canals. When spacecraft finally arrived, they found a cold, dry world, its atmosphere thin and unbreathable, its surface barren but marked by the traces of ancient rivers. The evidence suggested that Mars had once been warmer and wetter, a world where liquid water had flowed freely. It was no longer alive in the way once imagined, but it bore the memory of habitability. Similar stories emerged elsewhere. Moons like Europa and Enceladus revealed subsurface oceans, heated by tidal forces and containing complex chemistry. Even Titan, with its methane lakes and nitrogen air, demonstrated that nature invents environments in which energy and matter interact in ways unfamiliar yet organized. These discoveries reshaped the concept of life's potential. It was no longer confined to planets like Earth, orbiting within narrow zones of temperature. Life, or the potential for it, might arise in oceans sealed beneath ice, in clouds above gas giants, or even within the depths of rocky interiors warmed by decay. The conditions for biology turned out to be more flexible than once assumed. Wherever energy can flow and chemistry can evolve complexity, the possibility of life remains open. Beyond our solar system, the question widened to scales almost beyond comprehension. If planets are common, then environments suitable for life must also be common. The laws of physics and chemistry are universal. Carbon, hydrogen, oxygen, and nitrogen, the essential elements of life on Earth, exist everywhere. Water forms naturally wherever conditions allow. Organic molecules appear in interstellar clouds, on comets, and in meteorites. The building blocks of life are not unique to one planet. They are part of the fabric of the galaxy. In the 1960s, as radio astronomy matured, scientists began to consider how to search for signs of intelligent life directly. The idea was simple. If other civilizations existed, they might use radio waves for communication, and those signals could, in principle, be detected. The search for extraterrestrial intelligence, or SETI, began with antennas pointed at nearby stars, listening for patterns that nature does not produce. The early efforts were modest, limited by technology and time, but they marked the beginning of a new kind of astronomy, one that listened instead of looked. No confirmed signals have yet been found, but the absence of detection does not imply emptiness. The galaxy is vast, and the timescales involved are immense. Civilizations may arise and vanish, their signals lasting only briefly compared to the lifetime of stars. The challenge is not only distance but duration. To detect another intelligent species requires overlapping moments in history, when both are transmitting and listening at the same time. The odds are low, but the potential reward, confirmation that life is not unique, is enough to sustain the search. Astrobiology, the scientific study of life in the universe, has grown alongside these efforts. It combines astronomy, chemistry, biology, and geology into a single pursuit, understanding the conditions that allow matter to become living. Its questions are simple but profound. How does life begin? How does it adapt to extremes? How long can it persist once it appears? On Earth, life exists in boiling vents, frozen deserts, and deep underground rocks. It thrives in conditions once thought impossible. These examples expand the definition of habitability, suggesting that life may be less fragile and more persistent than once believed. The discovery of exoplanets has given astrobiology its laboratory. Each new world represents a potential experiment in chemistry under different conditions. The search for biosignatures, chemical imbalances in atmospheres that indicate ongoing biological processes, has become one of the central goals of modern astronomy. When a planet passes in front of its star, the light that filters through its atmosphere carries fingerprints of its composition. By studying those fingerprints, astronomers can detect gases like oxygen, ozone, methane, and carbon dioxide. Certain combinations, particularly those that coexist out of equilibrium, suggest continuous replenishment. On Earth, such replenishment comes from life. Future telescopes are being designed specifically for this purpose. Instruments capable of separating the faint light of a planet from the overwhelming glare of its star will analyse spectra in unprecedented detail. They will not look for signals or messages, but for chemistry, patterns of molecules that cannot be explained by simple geophysics alone. The detection of even one such atmosphere would mark a turning point, transforming speculation into observation. The galaxy would no longer be a place of potential life, but of confirmed life, varied and distant yet real. While technology advances, the philosophical weight of the question deepens. The realization that planets are everywhere forces a reconsideration of probability. If the Milky Way contains hundreds of billions of planets, and if even a small fraction lie within habitable zones, then statistically, some must host life. The silence we perceive may therefore be temporary, a result of our limited reach, not an absence of others. The Drake equation, formulated in the 1960s, remains a framework for this reasoning. It expresses the number of detectable civilizations as a product of multiple factors: the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction where life actually appears, the fraction that develops intelligence, the fraction that chooses to communicate, and the length of time such civilizations remain detectable. Many of these factors remain unknown, but each discovery narrows the uncertainty. The search for microbial life is more immediate. Missions to Mars, Europa, and Enceladus aim to detect signs of biological activity directly. These worlds are within reach, their surfaces or plumes accessible to probes. If life is found in even one other location within the solar system, it would imply that life arises readily wherever conditions allow. The conclusion would echo across the galaxy, suggesting that the emergence of biology is not a rare event, but a natural consequence of physics and chemistry. The question of whether we are alone is not only scientific, but existential. It touches on the way humanity perceives itself within the universe. For most of history, life on Earth was assumed to be the centre of meaning. The Copernican revolution displaced that centre physically, showing that Earth orbits the Sun rather than the other way around. The discoveries of modern astronomy continue that displacement, expanding the frame outward until there is no centre at all, only continuity. Life, in this view, is a phenomenon of the cosmos itself, one that emerges wherever conditions are right. If intelligent life exists elsewhere, its forms and perceptions may be beyond our imagining. Evolution adapts organisms to their environments, and those environments vary infinitely. Some civilizations may live under thick clouds on perpetual night worlds. Others may evolve beneath oceans or within ice. Their senses, technologies, and modes of thought could differ completely from ours. Yet the fact of their existence would still bind them to the same physical laws that govern us. Gravity, chemistry, and time shape all forms of matter, and through those shared foundations, a kind of kinship would exist across the void. The search for such kinship continues through multiple avenues. Radio telescopes scan the sky for narrowband signals that nature does not produce. Optical telescopes look for laser pulses that might serve as beacons. Infrared surveys monitor stars for unusual patterns of light that could indicate large structures or technological activity. Each approach extends humanity's listening. None have yet yielded confirmation, but the silence carries its own information. It sets limits, defines parameters, and refines where and how to look next. Some researchers propose that the rarity of advanced civilizations could be a matter of timing. The universe is still young compared to its potential lifespan. Stars like the Sun will continue to form for trillions of years. The conditions for life may become even more favourable in the distant future as elements accumulate and environments stabilise. In that context, humanity may belong to an early generation of civilizations, born in a cosmos still finding its equilibrium. The absence of others might not mean isolation, but precedence. Even without direct contact, the search itself has value. It connects the study of planets, stars, and galaxies with the study of life. unifying fields once considered separate. It transforms astronomy from a science of distant objects into a science of potential connections. Every spectrum analysed, every light curve recorded carries the possibility of revealing not only another planet but another context for existence. In the meantime, life on Earth remains the only confirmed example. Its diversity, resilience, and adaptability serve as the template for imagining what might exist elsewhere. The study of extremophils, organisms that thrive in environments of acid, radiation, or pressure, demonstrates that life does not require comfort, only opportunity. Wherever energy flows and molecules can assemble, complexity can emerge. The same logic that applies here must apply everywhere. The question of whether we are alone, therefore, may not be answered by a single discovery, but by a gradual accumulation of evidence. Each new detection of an exoplanet atmosphere, each chemical signature hinting at imbalance, adds weight to the probability that life exists elsewhere. Even if no other civilization is ever found, the knowledge that the universe creates habitable worlds by the billions changes the meaning of solitude. It replaces isolation with participation, reminding us that life, once begun, is part of a larger continuum. As telescopes continue to reach farther and instruments become more sensitive, the boundary between speculation and detection narrows. One day, a faint signal or a chemical spectrum may show the unmistakable signs of life. When that moment arrives, it will not be an ending but an expansion. The galaxy will remain as vast and complex as before, but the awareness of companionship, of other living systems under other suns, will alter how humanity perceives the night. Until then, the search continues, steady and methodical. Radio antennas listen through static. Space telescopes dissect starlight. Probes traverse the solar system, sampling ice, dust, and vapour. Each act of measurement contributes to a single unfolding effort to understand whether the phenomenon of life, so intricate and improbable on one world, is woven into the pattern of the cosmos itself. The evidence grows quietly, line by line, spectrum by spectrum, until one day it may reveal that the universe is not silent, but shared. Between the countless points of light that fill the sky, there lies a darkness that seems empty but is not. It is a medium rather than a void, a quiet stretch of space through which all things move. The stars, the planets, the dust, and the unseen matter that binds them are suspended within it, each separated by distances so immense that even light requires years to cross them. Yet this distance does not signify isolation. It is the structure of the galaxy itself, the quiet between stars that holds the rhythm of their motion and the memory of their creation. When viewed from Earth, the night sky appears still. The constellations seem permanent, their shapes familiar across generations. But this apparent stillness is an illusion of perspective. Every star is in motion, orbiting the centre of the galaxy along vast trajectories, drifting slowly relative to one another. Over millions of years, the patterns of the sky change, constellations dissolve, and new ones form. The spaces between the stars expand and contract as they move through their orbits. The quiet is not silence, but balance, a slow motion too vast for human senses to perceive. Between these moving lights lies the interstellar medium, a mixture of gas, dust, and magnetic fields that fills the galactic disk. It is tenuous beyond comprehension, on average a few atoms per cubic centimetre, but it is not empty. It carries the residue of stars that have lived and died, the ashes of supernovae dispersed across space. Within that material are the elements that form planets and life: carbon, oxygen, nitrogen, silicon, and iron. Every atom of every living thing on Earth once drifted through that medium, part of the quiet between stars. The space that seems lifeless is, in truth, the source of everything. The quiet also carries radiation, cosmic rays and background light that cross the galaxy in all directions. The faint glow of starlight scattered by dust, the echo of supernova explosions, and the far older remnant of the universe's beginning, the cosmic microwave background, all intermingle there. Space is not silent in a physical sense. It hums with energy, fluctuates with magnetic fields, and vibrates faintly with the movement of charged particles. The quiet between stars is the quiet of equilibrium, not of absence. When a star dies, it contributes to this equilibrium. The outer layers of the star are blown into space, forming nebulae that glow for thousands of years before dispersing. Those expanding shells of gas enrich the surrounding medium with heavier elements. Over time, new stars form from that enriched material, and with them, new planets. The cycle continues endlessly. Birth, life, death, and renewal. The quiet between stars is not a background, but a living process, a slow circulation of matter through the galaxy's vast body. In certain regions where density is higher, the interstellar medium collapses under its own gravity to form molecular clouds. These clouds, opaque to visible light, are the nurseries of new stars. Inside them, knots of material gather, heating as they contract until nuclear fusion ignites. Around these newborn stars, disks of gas and dust form, the precursors of planetary systems. Within those disks, collisions and coalescence begin again, shaping new worlds from old material. The quiet between stars gives birth to motion, and motion gives rise to structure. Even beyond the visible galaxy, the quiet continues. Intergalactic space stretches across millions of light years, thinner still, but filled with the same invisible threads of gravity and matter. The Milky Way itself drifts through that greater silence, moving toward the Andromeda Galaxy in a slow dance that will end, billions of years from now, in merger. The quiet between galaxies mirrors the quiet between stars. Not void, but space in which new forms emerge. Within this immensity, human life unfolds on a scale that barely registers in cosmic time. The signals we send, the telescopes we build, the orbits we trace, all are confined to a narrow band of awareness. Yet they reach outward, probing the quiet, measuring its depth. Radio waves from Earth expand through the galaxy, spreading at the speed of light. In 100 years they have travelled only a few dozen light years, a small bubble of awareness within a sea of darkness. The rest of the galaxy remains untouched by our presence, unhearing, unmoved, but within that bubble, the act of listening continues. The quiet between stars has become the medium of both observation and imagination. Every telescope depends on it. Every image of distant galaxies passes through it. Light travels unimpeded for millions of years, carrying the history of its source across that silent expanse. The clarity of the night sky, the crispness of starlight, depends on the emptiness between. Without that vast separation, there would be no perspective, no way to see the universe as a whole. The quiet is what makes the stars visible. In this way, the emptiness between worlds becomes a kind of mirror. It reflects the scale of existence, the measure of time and distance that defines reality beyond human life. The galaxy's structure, its motion, and its cycles of creation all depend on that space. The stars are not crowded but balanced, separated enough for their systems to remain stable. Planets can orbit safely because the distances between stars are so large. Life, where it appears, depends on that stability. The quiet between stars is not loneliness, but protection. Occasionally, those spaces are crossed. A star passes near another, altering orbits or exchanging comets. A rogue planet drifts through the outskirts of a system, pulled briefly by gravity before continuing on its way. Over billions of years, such encounters are inevitable but rare. The galaxy is large enough to keep its members mostly apart, close enough that their influence is shared. The The quiet allows motion without collision, interaction without chaos. The same quiet carries the remnants of things long gone. The light of stars that no longer exist still travels through it, arriving at distant worlds long after its source has faded. The radio waves of ancient supernovae continue outward, expanding forever. Even the photons from the first galaxies, born when the universe was young, still move through that space, stretched and cooled by the expansion of time. Every moment of cosmic history continues to exist somewhere within that quiet, preserved as light in transit. For astronomers, the quiet between stars is both obstacle and opportunity. It hides the objects they seek to study, dimming them with distance, but it also preserves them. Light travels in straight lines, unchanged except by gravity. A photon emitted from a star in the Andromeda Galaxy 2 million years ago arrives today as a messenger of what that galaxy was then. Every observation is an act of looking into the past through the quiet that has carried that light unbroken across ages. Within this framework, life on Earth and elsewhere exists in an interval of stillness. The planet moves around the sun moves through the galaxy, and the galaxy itself moves through the universe. But within each of these motions lies a temporary equilibrium. The quiet between stars sustains that equilibrium, giving each system the space it needs to endure. The balance is delicate yet persistent, maintained by gravity across unfathomable scales. As human technology extends its reach, probes and signals venture deeper into that quiet. The Voyager spacecraft, launched in the 20th century, are now beyond the influence of the sun's solar wind, moving through interstellar space. They carry with them recordings of sound, music and greetings, a gesture of curiosity sent into the silence. Around them, the density of matter is so low that years pass between collisions with individual atoms, yet their instruments still record faint signals, the whispers of particles and fields that fill the space between stars. Even in what appears to be emptiness, there is movement and interaction. The study of the interstellar medium continues to reveal its complexity. Magnetic fields thread through it, guiding charged particles. Shock waves from supernovae ripple across it, compressing gas and triggering new star formation. Cosmic rays travel through it at nearly the speed of light, influencing the chemistry of clouds and the surfaces of planets. The quiet is not static but dynamic, filled with invisible currents and waves. It is the background against which everything else unfolds. The quiet between stars also defines human perception of the night. When people look upward, they see the light of distant suns against a background of darkness, and that contrast gives shape to the experience of scale. The mind interprets the blackness as absence, but it is in that contrast that depth emerges. Without the quiet, there would be no way to separate one light from another, no sense of distance, no map of the sky. The darkness is what allows the stars to be seen as individuals. Over cosmic time, the quiet itself changes. The density of the interstellar medium fluctuates as stars form and die. The spiral arms of the galaxy pass through phases of greater and lesser activity. The Sun, in its long orbit, moves through these variations, encountering regions of higher radiation or greater density. These passages influence the solar system subtly, altering the outer boundaries of the heliosphere and the flow of cosmic rays that reach Earth. Even here, in the space between, interaction never ceases. On the smaller scales, the quiet is filled with fields and particles, each governed by quantum uncertainty. On the largest, it is shaped by gravity and motion. Between those extremes lies the environment in which galaxies evolve and planets orbit. The quiet is not emptiness, but the medium of continuity. Every photon that has ever been observed, every signal ever received has travelled through it. Every life that has ever existed has depended on it. To think of the quiet between stars as silence is to underestimate it. It is the connective tissue of the cosmos, the space that allows the stars to shine without interference. It is both the distance and the link between every point of light. The galaxy's structure, the cycles of birth and decay, the distribution of elements, and the very existence of planets all depend on it. The quiet is what holds the pattern together. Even now, as telescopes and instruments probe deeper into the universe, the quiet remains the constant backdrop. It expands as the universe expands, carrying galaxies farther apart, stretching light into longer wavelengths. Over billions of years that expansion will continue, and the stars themselves will fade. But the quiet will remain, filled with the remnants of light, the echoes of motion, and the memory of everything that once was. In the present, it surrounds every system, every orbit, and every motion. The planets move through it as dust moves through air suspended and carried along. The stars burn within it, illuminating only small regions of its expanse. The quiet between stars endures as the most consistent feature of existence, not emptiness, but the calm that allows creation to unfold.